So you guys, part two, we're gonna continue kind of where we were, starting with the semiconductors. And so without going too super crazy, remember semiconductors, we start to use those in what types of systems? Electrical systems, starting systems, what? It's more like electronics. So if you're dealing with computers and sensors, we're probably talking semiconductors. So right here, electronics, typically talking about device in which electrons are conducted through vacuum gas, or a semiconductor right here. So old school, we didn't really have semiconductors. So we were using more stuff like vacuum and gas. Interesting, semiconductors' electrical resistance is higher than most conductors, but lower than an insulator. Remember, it's kind of like, it's in between. And the cool thing is, we can make it like an insulator, we can make it like a conductor, depending on what we do. And so the conducting ability depends on two kinds of charge carriers. So the negative electron, this semiconductor contains an excess of free electrons that can be made to flow and carry a charge. Or the hole, which occurs when an electron moves from its existing place to a new place, leaving a void. So this, in automotive application, we're not typically looking at this as super important stuff to know. So the main takeaway is, if you more or less understand how the electronics work, we could diagnose them. If you want to be the person to design these systems, I'm not the guy to teach you that. That's not really my area of expertise. Typically when the customer comes in, they come to us with a concern. So like, for example, Refugio, you were talking about your airbag light is on. If we were to want to diagnose that vehicle, this type of information is not like super critical to that process. However, what you have to understand is, if we're diagnosing the airbag light, we got a few possibilities. One, it could be the airbag itself. Two, it could be the wiring. Or three, it could be the computer. So the computer, we don't want it to be a total mystery box that you're really afraid of. So the airbag basically has a squib, which is kind of like a, you know when, if you're gonna like light a firework, which I'm sure you'd never do, but let's just say you were going to do that because you had to save someone by lighting a firework or some heroic act. If you're gonna light the firework, you know that little thing, it's like a fuse? You light the fuse and then it burns. The squib is kind of like a fuse, and really what it is, we could measure it like a resistor. So what I'd love to do with the airbag concern is just measure the squib with the meter on ohms, and then you'd be like, is the squib good or bad? The problem is, when you do that, you can actually kind of like light the fuse, light the squib, and that could deploy the airbag. So the way that we diagnose airbags tends to be a bit confusing, because you can't use your meter on resistance to do it, because the 9-volt battery can actually deploy the airbag, right? So if we were to take a step back, and I were to say, it could be the airbag, cool, but we can't exactly measure that. So that makes it hard to diagnose, right? And then it could be the wires. We talked a little bit about the wires. The wires aren't that hard to diagnose, actually. You could measure resistance on the wires, but if you're gonna do that, you have to have the airbag out. It has to be disconnected. And so, Refugio, when you followed the diagnostic flow, it was saying you basically need these special adapters to take the airbag out and plug this fake airbag simulator in. Basically, it's a resistor. Cool. If you were to have the correct amount of resistance, the computer is going to see the correct amount of resistance, and it's going to be like, hey, there's no problem, right? But if it doesn't see the correct amount of resistance, it's going to set a fault, because it's saying, hey, there's something going on here. The computers can't tell if it's a wire, if it's the airbag itself, like the resistance on the squid. So with typical situations, the way that we go about the diagnosis is, it's process of elimination, and the thing we can't really eliminate is the computer. So the reason I want to focus on that is, if you have an airbag problem or a sensor problem or something, basically what we're doing is we're checking the sensor or the airbag, we're checking the wiring, and then if those are good, we're kind of assuming it's the computer. And inside, it's all semiconductor, small scale electronics and printed circuit boards, and they can fail. but it's not really all that often. And the big problem is this is expensive. And if you're kind of like, well, I think it's a computer, and you put a computer in it, you just spent a lot of money, and if it doesn't fix it, you know, that's what we're trying to avoid, right? So as we discuss this, don't feel like you're like, I need to understand the difference between the negative electron and the hole. You just want to have an overall understanding of sort of what's going on in that computer so that you're not too afraid of it, so that you can diagnose it, okay, to give it some good context. Now as we continue, like again, the overarching theme, as we want to make this semiconductor work for us, it's saying the number of charge carriers can be altered, okay, interesting, by adding very small quantities of impurities to a semiconductor material. So what they're doing in the labs is they're slightly changing these. They're engineering these to be able to do different things. And one of the upcoming slides is a transistor, so you're just going to get an overall understanding of the transistor. That's a big part of what's in the computer. And then a doped semiconductors always has an excess of a charge carrier. So now we get into the P and N type, N and P or P and N. So they're just different types. Electrons in excess make an N, and holes in excess make a P. So do you need to be able to define these two on the spot? Probably not. But when you're really deep in the service manual and it says it's a P type or an N type, you'll be like, oh yeah, I know there's two types. I don't totally remember what the differences are, but you'll see P and N, and I don't want you to be like, what the heck is that? Right, so if you look, N, electrons in excess. P, holes in excess. Those are the two differences. Okay, so if you look at what that, if you were to put this under a microscope and be able to identify the different molecules, you'd see the N type and the P type. And so what's this relating to? And you can see they're using some interesting molecule, like there's an arsenic atom in this one, there's a boron atom in this one. This one has a free unbound electron, and this one has a missing electron, right? So the whole, now what this means to you practically fixing the car, not a whole lot, not a whole lot. But you at least want to be like, oh yeah, there's a P and the N type, and this is made in the lab different. Remember how they're adding impurities, they're like injecting and doing some different modification in the lab. This is really what they're talking about. Right here. Okay, and then this is actually a transistor, so we could get like super in detail as to exactly how this works, but I'm going to give you the overall. Okay. The point where P and N type semiconductors join is called the P-N junction. So if we do an N material, and then a P material, and then an N material, so it's kind of like a sandwich, right? Like bread, what's in the middle? Which one? I don't know. Peanut butter it is. That's why it says P. Of course, that's what it stands for. If we do this, we could do something really cool, okay? So there's some electrons in holes, they'll cancel each other out, etc. The depletion layer is a very thin layer that acts like an insulator. Here's what you need to know. In automotive, we use things called relays, and we can basically control a relay using a little bit of electricity to ultimately control a lot of electricity. I'll give you a quick example. Let's say it's headlights. You guys, in the newer cars, there's typically a small little headlight right here, a headlight switch. That is not a switch that's designed to carry 20 amps. But when your headlights and all your lights are on, you may very well have, maybe 10. You may have 10, 15, 20 amps flowing through there. That would burn out that switch. So we don't make all the electrons flow through the switch. What we do, we make a small amount of electrons flow through the switch, and when you turn the switch on, it makes low amps. Remember the terms, right? Amperage, current flow. It uses just a little bit of current to go through the switch, and that little bit of current controls a thing called a relay. And that relay will actually control a bigger part of the relay. So the small part can have a low current flow, And if it sends low current flow through the small part of the relay, it'll go click, it'll latch, and then we'll take a bigger wire and we'll send it to the side of the relay, and then if the relay is closed, it'll send the high amperage out to the headlights. Cool, so we're gonna cover relays in a little bit more detail, but if you kind of understand what I'm saying, we use relays so that we can use a small amount of electricity to control a big amount of electricity. We don't necessarily wanna have a really big light switch, cool? Go ahead.
So these materials are inside a relay? Or
Okay,
what?
pause.
Okay.
Relay is electrical, not electronic. So a relay was a mechanical thing. There's an actual switch that comes over, they click, they make noise. There's moving parts. The negative of moving parts is moving parts wear out. And relays also take up kind of a lot of space and stuff, okay? But the point of a relay, we can use a little bit of current flow to control a lot of current flow, cool? Now pause that same exact concept. We can do a similar thing with a transistor, okay? If we want current to flow from C to E, big current right here, we can control that with a little current right here. That's what's kind of cool. That's mainly what a computer does when we use transistors. So if you were to have your big 12-volt battery right here, and you were gonna send current through your big LED lights from Baja Designs or something, you could use a relay, but if you wanted to be pretty cool, you could actually do what's called solid state. Solid state doesn't have the moving parts. Solid state doesn't have, a relay needs to have contactors, and the contactors over time, they can kind of burn and arc, and they can have resistance and stuff, right? So we could eliminate the relay. We could have 12 volts come in on C. We could have your big Baja Designs LEDs on E. How do you turn them on and off? You just use a little tiny bit of current right here on B, and the computer can do that. So now if we go to a more modern car, who's got headlights that turn themselves on and off? All right, so if you had an old car, turn the headlights on and off, you used a switch. If you had a really old car, sometimes it was like a big knob, that's heavy, that's a lot of amps. If you want the computer to be able to turn the headlights on and off, we want to use something like this. This is tiny, tiny, tiny. It can go inside of an ECM or like any kind of computer, right? And then we can have just a tiny little bit of electrons, a little bit of current flow, control a lot of current flow. The computer is like totally happy with controlling B.
How do those newer lights know when it's dark?
Okay, now that's what I'm saying for a transistor being a semiconductor is true. We can also do semiconductor stuff to make sensors, and so if we were to do what's called a photodiode, we can use, it's kind of similar to this actually. If light comes in, we can make this semiconductor flow electricity, and we can do that several times, and then we can approximate the amount of light that's coming in. And then what we'll do is we'll actually make that whole thing into a sensor called like an ambient light sensor. We'll put it up on the dashboard, kind of under the windshield. And then if there's a little bit of light, these semiconductors will send a small amount of electricity back to the computer. But if there's a lot of light, it'll send a lot of electricity back to the computer. When it gets dark out, it'll send like no electricity to the computer, and the computer will say, hey, there's no current flow off of the ambient light sensor. You know what that means? Turn on the headlights. How does it turn on the headlights? All the computer's got to do is send a little current on B, and then that'll allow the big 12 volts on C to make it all the way to E and light your headlights up. Cool? It does it without clicks. It does it without sound. You can't change a transistor. The transistor is in the circuit board. All right, so if this transistor is defective and your headlights don't come on, what's the fix? You tell me if you understood what I'm saying.
The relay.
But this isn't
Oh, okay.
replaceable. Exactly, the new computer. Bingo. But you better be sure about it. See, so that's what I'm saying. If you were to ask me, I don't know how to engineer this stuff. Like, I'm totally lost. There's a lot of stuff I know how to do, but this is not, actually, I wish Tim was here. This is what Tim does professionally. You guys remember Tim. This is literally his job. He's tells me, I do this type of work on the chip level. He told me he did a chip that he put in a computer to do this type of work. I don't know the details. He had to do 3,000 tests on that circuit board to make sure that that circuit board would do exactly what it's supposed to do. That's not my area of expertise, but I find it really fascinating, you know, because if it's defective, right, I get a new computer and I plug it in there and I program it and it works. I'm like, yeah, but he's the guy who designed it and did 3,000 tests to make sure if the ambient light sensor sees low lighting conditions, it should apply a current on B and make the high current go through here. Next thing you know, your headlights are on, right? That's just amazing to me. So if we were to put this thing in reverse, back up, old school cars, if you wanted to turn the headlights on, you had to do that sucker. You had to do it. You had to literally turn the switch. When you turn the switch, you remember if we were to back up what the switch looks like, right? You turn the switch, and you were closing this switch up here. That was your job. Now on a newer vehicle, technically, we could skip that, and the computer controls B. The computer closes the switch, but the switch isn't like this. The switch is like nothing moved in here. Nothing went click. Nothing spun. Nothing. That's why it's solid state. It just doesn't flow current. But if you apply current here, it does flow current. Kind of get what I'm saying? This is wild. So when you hear the term solid state electronics, you're looking at stacks and stacks and stacks of these. And they can turn things on and turn things off. And basically, remember, that's what a computer does. It's on and off. It's zeros and ones. This one's on, this one's off, this one's on, this one's off, this one's on, this one's off. That means something. And then if you really want to get outside my comfort zone, computers will do that with thousands, I don't know how many of these, thousands and thousands. And depending on their position, will indicate a number or letter. And then you get into hexadecimal code. And then a whole bunch of these in different positions will make a different hexadecimal code. So if we were to zoom out and go onto the network, one of the things we would get into in electrical too is like the CAN bus network. The CAN bus is where you have a whole bunch, 40, 50 computers on a network. And let's just say it was your brake lights, for example. Your brake lights should come on when you press your brake pedal, right? But also your ABS system needs to know about your brake pedal. Your transmission needs to know about your brake pedal. All these computers really need to know, are you depressing the brake pedal or not? Depressing means pressing down, okay? It doesn't mean not pressing. Depressing is like to push it down. If the brake pedal's depressed, we not only want the brake lights on, we want the ABS to know about it, we want the automatic transmission to know about it, we want the cruise control to know about it, we want the engine, everybody needs to know. So what they would do on old school is they'd have a brake light switch with a whole bunch of wires going to it, and when you step on the pedal, it would close like 2 or 3 switches, and these computers would be like, oh, the switch is closed. But now it's more efficient, okay, but it does make it a bit more difficult to diagnose. They have one brake light switch, and that brake light switch will go to, I don't know, let's pick one module, right? There's 50 of them. It goes to the body control module. If the brake light switch is closed, the body control module senses it, and then the body control module using transistors will make a hexadecimal code and broadcast it out on the network. So if there's a hexadecimal code, I don't know, the XYRB1275, of course I know what that means. You know what that means? Brake light switch just closed, and all the other 49 computers know that code. So when they see that code broadcasted, that hexadecimal code, what do you think that means?
It's closing.
Yeah, the brake light switch is closed. Like the body control module is like, oh yeah, I know what that means to do. Turn on the brake lights. The ABS module is like, oh, I know what that means to do. Get ready for ABS activation because maybe the wheels are about to lock up. The automatic transmission knows what that means. It's going to be like, hey, brake switch is on. I need to disengage the torque converter clutch. We could go on and on, right? We could go on and on. But now once we get into the solid state electronics and we can use thousands of these transistors to actually make messages, we no longer have to have mechanical switches. And that's why we could do so many cool things with the lights. My phone's videoing, so I can't show you, but if I were to pull up the Tesla app on my phone, or even the My Chevrolet app, if you guys want to be like, they're both American car companies, just for record. But if you want to be cooler, I could pull the My Chevrolet app. I could make my Camaro beep the horn at my house right now from my phone. How? You know, that's magic. Actually, it's not. It's simple. The horn is ultimately controlled by a transistor. That transistor can get messages from other things. I can do that, and even OnStar. Did you know OnStar could unlock your car? How? Like, there's an OnStar module that's linked to a satellite. The people on the OnStar call center will verify your identity and be like, oh, you want me to unlock the car? No problem. Boop. Then satellite sends this beam down to the car, magical beam, of course.
So it's just like when you turn on your car from the
Yeah,
inside,
sure.
from the inside your house.
Once you integrate the solid state electronics, you can control so many things without having to have anybody in there pulling levers and flipping switches and stuff, right? So if OnStar sends a signal on the satellite, then the OnStar control module, which I think is called a communications module, remote communications, RCM, remote communications module, sees that and it's like, oh, the OnStar rep just said unlock the doors. It broadcasts out that code, right? And then the body control module sees it and it's like, oh, I know what that means. XYZ1234, that means unlock the doors. Send a little bit of current, positive comes in, positive goes out, unlocks the doors. Click, right? Now we could do that from the remote, we could do it from the switch, we could do it from the OnStar, I could do it from the app on my phone. All we're doing is really controlling this transistor, make sense? So there's so many potential things that we could do once you get into the electronics aspect.
So it's basically how I understand it. The B is just like a wake up call, just a little jolt.
So
to
like
wake it
if
up.
we were to compare this to a relay, remember in the
Yeah.
relay we use a little current to control a lot of current? Right here, we're using a little current to control a lot of current. Now the science as to why, I don't totally understand, to be quite honest with you. But there's somehow when we send small current, it rearranges these atoms and it allows current to flow. Remember, it's a semiconductor. It can be an insulator or a conductor. We're like, what? No current, it's an insulator. Current on B, it's a conductor and you're turning stuff on and off. And that's basically, you know, what I could do is diagnose the cars, because that's my training, but that's also my experience, right? So exactly how, under the microscope, I don't really know. However, if the car is not able to unlock the doors, and I'm able to go in with a computer, did you know I can command this transistor? I can go in and say, hey, unlock, 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 right? I can basically bypass the whole system. I can use the scan tool and say, well, what I'm really saying is, give me a current on B, give me a current on B. And if it still doesn't work, you know, I'm really like, hey, there's something up with that transistor. What do I need? New computer. But this is where you gotta watch out. Because what if this computer is not getting a signal, right? So I call OnStar, tell them, hey, unlock the doors, and OnStar sends the signal and it doesn't work. You could be like, yeah, clearly it's the transistor, it needs a computer. But what if the OnStar module is sending out a command on the network, right? It's sending out the XYZ123 hexadecimal code, but it's never making it to this computer, right? So I'm not totally sure if it's the computer. It could actually be the network wiring. So if you got your own laptops, right? They're mostly Wi-Fi. You know, in cars we don't do a whole lot of Wi-Fi. Wi-Fi can be a little unreliable, but more importantly, Wi-Fi is a little easier to hack. You know, so you know, cars are already getting stolen and stuff. So we don't want to make it even easier for someone to get on our Wi-Fi network of our car and be like, send out the hexadecimal code that says unlock the doors. You picking up what I'm putting down here? So most of the time they're hardwired. So when I'm going to give this example, I want you to go back to, remember when you plug in the cable to the computer? What cable do you call that? Ethernet. I'd go with Ethernet. Do you know some cars, some automotive vehicles use Ethernet for their networks? Tesla uses Ethernet. Ethernet and CAN are just different ways to do the network. So when we're talking about all these networks, right, that OnStar module to the body control module, they're all gonna be on an actual network. They all have a wire. They have two, actually, wires connected, boom. If you had your computer and let's say that there's 50 of them in this system, if you had 50 computers and you jumped on one, that one computer should be able to communicate with the 49. But if that one computer won't communicate with any of the 49, don't you think it might be the Ethernet cable to that computer you're trying to work at? Right, so we have to do some troubleshooting on the network. If you don't have a function, the locks, for example, you can't just be like, that's a computer. Yeah, it could be. But it could also be a problem with that Ethernet cable, which in this case is, on most cars, we've really gone to CAN, Control Area Network, okay? So when we're doing this type of diagnosis, you're never gonna get in there and be like, is it the boron atom or is it the arsenic atom? Because I don't actually totally even know how you figure that out. And it's not real important. What is important is, at the end of the day, the car came in with something that didn't work. You need to diagnose it and sell the right repair. Make sense? You don't really need to impress me with like, oh, that's an N-type or a P-type. It's a PNP transistor. It's an NPN transistor. This one's an NPN, okay? And that's cool. But like, really? You know what the customer wants to know? Do I need a wire repair? Do I need a computer? Do I need what do I need? What do I need? You'd be like PNP and NPN. You'd be like, I don't really get to. They're willing to give you their money, but you just got to provide a fix to them. Make sense? They don't care about the details. So for that, I've kind of adapted myself. You want diagnosis? I got you. Exactly the details. Maybe Tim got you. Okay, cool. So we'll kind of continue. Diodes are really interesting. Who's ever heard of a diode? Okay, pretty low numbers. Who's heard of LEDs? You've all heard of a diode. LED, light emitting diode. They're diodes. Lots of them. If you got LED TV, lots of them. If you got LED lights, I just put LED lights in a Tacoma Sunday. You know, nice, clean, white, almost like not quite blue, but like white lights. LEDs are nice. It's just another diode. Okay, so when we get into diodes, a diode is one P-type semiconductor material joined to one N-type. Make sense? Remember how the transistor was NPN or PNP? Those are transistors. We can turn things on and off. A diode is just an NP or a PN, you know, and what's interesting about that is current can only flow one way on a diode. Okay, so if you're more mechanical in the brain, which is typical, a diode would be a check valve. Who's ever heard of a check valve? If it's a water check valve, that means water can go this way, but it can't go this way. That's a check valve. Why do you want to do that? Well, we're here in a little bit of agriculture area here today. You smelt it on the way in, didn't you? You know what that smell is?
Fertilizer.
Money. Okay, so when you're dealing with that, right, because these are dairy farms and stuff, you don't really want that water getting back in the water supply, do you? You got cows stomping around and their own money. Okay, but that water's kind of dirty. So when it's agriculture, they make you put in a check valve. It's actually a double check valve. But when the water goes out, cool, no problem. But the water can't go back into the supply because by the time that the cows are drinking out of the trough, it could be contaminated. Cool? That's a check valve. Water out, yes. Water back in, no, we don't want that water. That water's got E. coli and, you know, diarrhea at a minimum. But maybe death too, potentially, yes. So, yucky stuff. Now, if it's air, we got air hoses out here. If you hook up the air hose to the power tool, air will go out, but it won't allow air to go back in. You know, we use check valves all the time. In electricity, if you want electricity to flow this way, but not this way, perfect, use a diode. That's what diodes do. How they do it? Well, that's what it's saying, right? It's a P and an N. Let's say it's a P-N junction. And then there's other types of diodes. So if it's connected to a voltage source, the P region is connected to the negative pole and the N to a positive pole. The negative pole attracts the holes, the positive attracts the electrons, And then because this enlarges the depletion layer and the insulation space, current cannot flow. Like, that's the scientific part. I'm not super passionate about exactly how it does it. What I can tell you though, if a diode is defective, one of two things will happen. And I think there's actually pictures. No. If a diode's defective, remember how the current flow should go this way, but not go this way? If a diode's defective, there could be two failures. One, nothing will flow through at all. The diode's like completely open. No current will flow. If we need that diode for, let's say, an AC compressor clutch and no current will flow, guess what? Guess what won't happen? That AC compressor clutch needs the current flow to magnetize, to make your AC compressor go pump, 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 so you can feel nice and cool. If it's open internally and the current flow never makes it, what happens to the customer's AC compressor?
It doesn't blow cold.
It don't go pump, 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 and they got warm air, right? So the customer comes to you and they're not like, hey, can you explain a PN junction? And they'll be like, when I turn my AC, I'm still sweating. All right, no problem, let me diagnose that. That could be the AC compressor clutch diode, right? So we need to be able to test it. Is it failed where no current will flow through either way? That does happen. That'll make this, whatever the component that it's connected to, it won't get current flow. If it's a light, the light won't work. If it's a motor, the motor won't run. If it's a solenoid, the solenoid won't activate. If it's a compressor clutch that works on magnetism, it won't get magnetized. Cool? So that would basically be like an open. We could check that with our meter. And that's pretty easy. You could do a voltage drop or available voltage test. It's just like testing for a switch that's not good or something. But there's another failure. Remember how current should flow this way, but not this way? Sometimes they fail where current can flow this way and flow this way. And that would cause a different thing. Actually, in the case of the compressor clutch, it's not that the AC compressor clutch wouldn't work. It's that the reason that diode is there is when the compressor clutch opens and closes, it makes like a little voltage spike. Do you think the computer's happy with said voltage spike?
No.
No, the computer's going to be like, dead. And then guess what? That little transistor is going to be like, it's going to be, let me translate this, Gen Z, right? Cooked. That transistor's cooked. So when we need a skibbity transistor, but we got a cooked transistor, that means that, see, it makes sense, the computer is going to fail. And then you're going to diagnose it and be like, hey, it's actually not the diode was working, but the computer's bad. Well, you got to check the diode in two ways. You got to make sure current can flow through the diode, but you got to make sure that current won't flow back through the diode. Because if it does flow back through the diode, it'll allow the computer transistor to fail. Then you'll put a new computer, and guess what's going to happen to the new computer? It's going to fail again. And you could be like, this is unbelievable. It was a defective computer, and the second computer. You know what'll fix it? Probably a third computer. Oh, no, wait. Maybe third time's a charm. Fourth is a dream or something like. No, you could keep putting computers in it, but then eventually it's got to go to a technician who actually knows some stuff, and they're gonna be like, this driver or this transistor shouldn't be failing like this. Let's check the diode. Oh wow, the diode flows this way, but it also flows this way. That diode is like a overcurrent or a high voltage suppressant. Sometimes they'll call it a clamping diode. Make sense? So again, the practical isn't so much about the it's about the why is the diode even there in the first place? The diode is to prevent voltage from current from going in the wrong direction. You know, voltage spikes, these types of things. And we'll get into the LED a little bit later. LEDs are cool because if you flow current this way, it makes a light, but it won't flow current this way. It's pretty cool. And then there's even Zener diodes. We'll get more into it, okay? And again, as we discussed, semiconductors, electronic components, that's what they do. Now, if you understand this statement, you're probably pretty good. Conductivity can be manipulated and controlled by doping with impurities to make transistors. So what they're kind of saying is like, the people in the lab figure out little mixtures and whatever the heck the engineers do, and then next thing you know, they can make it more conductive. We can manipulate it to be conductive or an insulator, conductor, insulator, right? We can do these different things with that NPN, and if we're controlling the P, it'll flow current. That's kind of what it's saying. That's the main deal with semiconductors. They can also vary their conductance. So Hall effect, okay. Hall effect's actually something that's hard to, we could spend 30 minutes on Hall effect. We won't. Hall effect is really useful to determine if there's a piece of metal close by to the sensor or not. So I'll give you an example. If we're talking about a wheel speed sensor, right? You know how your wheel turns like this? Cool. We'll put little teeth on a wheel in there, and then we'll put a sensor next to it. These Hall effect devices are really accurate at telling is there a tooth there or not. So if we do a wheel, right, and it's tooth, no tooth, tooth, no tooth, it can tell if there's a tooth because of this Hall effect. The Hall effect varies a magnetic field. It's all solid state, it's semiconductors. And let's just say that you're going slow, you're gonna see like tooth, no tooth, tooth, no tooth. But what happens when you go fast? Tooth, no tooth, 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 tooth. Right, so we can use this Hall effect design in speed and position sensors. If you want to know the position of something, Hall effect is amazing. If you want to know the speed of something, Hall effect is amazing. And it's very, very, very precise. So let's say we were to go into the future and you were to find out the steering wheel that you're turning is connected to nothing. The steering wheel that you move is just moving a sensor. And that sensor is giving a signal to a computer, and that computer is controlling your wheels. And you have no connection to your wheels. Are you afraid yet?
Yes.
That happens now. This isn't the future. That was like 2 years ago. Not on probably all your cars, but there is like a RZ450, Lexus EV, no connection at all. You know what's really cool about that system though? Let's say that, you know, if you're going down the highway, you want like a really tight, you want a little leeway to move the steering wheel a bit, but like if you go around a turn, you want it to turn more. It's almost like, imagine it could be a variable ratio where right here you're fine tuning it, but if you turn it this far, it'll have your wheels turn like super far and you can do a quick U-turn. The system can do that. If you have a regular connection, you got to turn the wheel a lot more. All right, let's make it even more interesting. Do you want the car to be able to drive itself or not?
No.
Oh, okay. Oh, never mind. Anybody? I got that.
I feel like we get so wrapped up in the can we do this that we don't really consider should we do this for a lot of stuff.
Perhaps.
There's on the news that the guy got trapped in a Waymo car who was just going in circles in the parking lot because it didn't know the exit and didn't know what to stop.
All right. We got people who are supposed to tell us what's right and wrong. For us, we're just supposed to be able to diagnose what's already been done. So I guess I'll focus on that. You may not want it, but somebody wants that car that drives itself. Okay, so if it requires a body to be in there turning the wheel, that's like, okay. But if we're trying to have it drive itself, don't you think the speed and position sensor would be helpful, right? So we can have a computer moving the steering wheel, and a very accurate Hall effect sensor can be telling you exactly where the steering wheel is and fine tuning it, be like turn a little more, or turn a little less, right? It doesn't even have to have eyes. The position can be so accurate. Cool. So whether you like it or not, but your points are taken. Your points are taken. Whether you like it or not, this is the stuff you're gonna work on. I'm just letting you know. I'm sorry to tell you. So you don't have to know everything, but if you read about a Hall effect sensor, you'd be like, oh yeah, that's like an electronic device that tells speed and position. And we could get into tons of detail, but I'll just leave it at that, cool? Semiconductors used to make sensors too. Remember we talked a little bit about that ambient light sensor. Oh, and look at this. Can vary their light to make photoelectric diodes and transistors. Cool? They're small, light, use low operating voltages. All this is a really big positive because when you're talking about computers, these can't handle high current flow. They also can't handle high voltage. So computers are really happy with this solid state type of sensors. Makes sense? Like Sensors that require a lot of amps, a lot of electron flow, computers like, ooh, I have little tiny printed circuit boards. It's like, I can't handle too much current flow. If we were to make it look like water, it's almost like these tiny little pipes and passages, and then you wanna get in there and send a fire hose to it, let me know how that system's gonna work out. They can't handle that much.
Don't like LED lights use less voltages than
Bingo.
but how
Current.
how is it? Oh yeah, current. How is it way brighter then?
And that's the thing that's pretty amazing.
Uh-huh.
Like with if you had a regular incandescent bulb, right? We got one filament that's made of tungsten or something. I don't know. We send a bunch of electricity through there and it makes some light. With a diode, we send just a tiny little bit. What's kind of cool, we can send a tiny little bit and have it be the most electricity efficient thing ever. Or we can have one and another one and another one and another one and another one. You could have 10 different LED chips in the size of that regular bulb, whereas your incandescent bulb's got one filament. Have a nice day. So they'll pack multiple LED chips on there, and then you're actually getting more light. It's still more efficient, but it is, every chip that you add is going to add more and more current flow, but it's still less than incandescent. So like, to me, I like the LED
I do too.
bulbs. For a house, I like it because it's lower electric bill. For cars, I like it because it's more light. By off-roading and stuff like that, big LEDs. So yeah, they're just more efficient. It is what it is. You know, there's
Let there be light.
yeah, but bright white light in a 6,000 K frequency and LED, I'm all about it.
It's
Love
great for when you have Ferraris doing dumb shit in front of you.
Oh dear, I'm just moving away from that. Now, what do you think's all happening here? We're on a grounded static mat, and there's a static strap. Why do you think?
No electricity.
Cool, you're getting there. You're getting there. Remember, this doesn't like high voltage or high current. You ever rub your feet on the carpet, and then you go, and you shock somebody? That would kill this. This would be dead. This whole thing might not be dead, but one individual transistor in there might go, let the magic smoke out. Now that one individual transistor is defective, something doesn't work. What is it? I don't know. Maybe it's the headlights, maybe it's the locks, maybe something, right? What do we need to do if one transistor is no good?
Replace it.
Replace what?
The transistor.
We can't. Well, I'll give you the benefit of the doubt. If you had the skills, you could disassemble that ECM and you could locate that transistor. Maybe you could rework it or something, but these transistors are so small you really can't even hardly see them. So we're replacing the whole computer. As technicians, that's what we do. Tim does different stuff. There are some places that will refurbish that ECU. So if you diagnose it and you're like, oh yeah, it's got a bad transistor, and you send it to a place, they may have someone in a little shop with this static mat and with these things, and they may be in their pinpoint soldering. You know, that's a real possibility. That's not what I'm training you to do. There's not really a whole lot of those jobs. That's not what this class is all about. So if we have a bad transistor due to shock, it's getting a new ECM. They could be $250. They could be $2,000. Could be anywhere in that range. So when we're working on this, you just got to be conscious that we don't even go inside them really anyway, but just to show you just how sensitive it is, if you are going inside them, you need to ground yourself because you might actually get a little static little.
And how does
and
that
kill
work
it.
though? How does the static strap work?
This grounds you. Okay, so you guys ever seen some of the videos where somebody is at the gas station, they go to like touch the nozzle and then bang, they're on fire and everything's all scary and stuff? That was almost every time it's static electricity. The phones are phones freak people out, but like your phone doesn't really have a whole lot of high voltage. But if you slide off your seat, you slide off, and you go to touch the nozzle, and you're built up with like a negative charge, and that's got more of a neutral charge, and you will discharge. And discharging is good, but when you discharge if there's a gap right there, there can be an arc of electricity, and that can ignite fuel vapor, not liquid, vapor. When you're fueling the vehicle, there's fuel vapor. The worst thing you could do is almost touch that nozzle and cause a little arc right there. Bada bing, bada boom. So what this does, it grounds it. So if you have a buildup of, we'll call positive or negative, whatever, depending on which theory. If you have a buildup right here, this will automatically drain it to the ground. Cool? the best thing you could do when you go to pump the gas, it does actually say discharge yourself first or whatever. You could actually touch a metal ground. You could just be like this, doop, and then go to the nozzle. And if somebody sees you do that, they'll be like, that person is so weird. They're probably stupid. Their intelligence is low. But like, actually, that would mean you understand what's really happening, you know? So a couple times I'll jump up in my truck with the gas jugs and I'll pull into Costco and they'll get the workers are kind of nervous, like you better not fuel those up in there. And I'm kind of like, chill, dude, I got it. I'll pull them out, put them on the ground, touch the metal, and then when they see me do that, they'll kind of like back off. They've been trained on the safety part, but your common person in the car, they don't know. So it's kind of the same idea. If you wanted to make it super safe, you know what you could do? Now this I'd probably laugh at you if you did this, but you could carry a grounding strap. When you get out, you could put it on your wrist and then you could clip it to something metal and you can have this nice wand and you can be like, you know, then I'd be like, all right, that's a little excessive. But as a matter of fact, that would be the safest thing you could do. You have no ability to charge yourself with a high voltage and actually cause a little arc. That's all this is doing. Where's grounding? You remember those things? It makes you healthier or whatever. You could get one of those grounding straps and you could work on electronics and you could also allegedly heal all of your physical ailments. And you know what it's all caused by? It's all caused by shoes. You weren't made to wear shoes. You were supposed to be barefoot. And when you were barefoot, it was supposed to drain your high voltage into the earth. And now you're insulated because your shoes are rubber and you need to run around. Oh yeah, I get the pop-ups. But the problem is I understand them too much, so that's kind of the thing. You could ground yourself through a strap. And actually doing electronics, we are supposed to do that. Cool. So again, I don't go nuts on this, but just seeing the semiconductors, silicon is the most widely used semiconductor. Where have you heard of, not silicone, but silicon?
Silicon Valley.
Silicon Valley. Why they call it that though? Silicon Valley.
Technology.
But that's what I'm saying. It's the semiconductors, the most commonly used being silicon. So they're making chips and technology and computerized stuff. That's Silicon Valley. That's why they call it Silicon Valley. They're doing a whole lot of semiconductor work over there. Silicon being one of the most common ones. It's got a useful temperature range. It's abundant. It's cheap. It's easy to manufacture. Cool. Germanium was used before that. Sometimes we'll use like gallium arsenide, silicon carbide, especially silicon carbide for blue light emitting diodes. Then they can withstand high operating temperatures. So they're taking materials off the periodic table of elements. Sometimes they're, doping them. They're doing some modification, and they're making them do like some really cool stuff. And that's what that's what I imagine is happening in Silicon Valley. I don't exactly know what's happening, but something. And those jobs were booming, and then there was kind of a fall though. Like this stuff is all on the design of it, and I'm not your guy, honestly. But fixing that broken junk, I could do that. I end up working on all sorts of stuff. Refrigerators, washers and dryers. I don't do it for everybody else, but if something of mine breaks, it's very irritating for me to hire someone. So I do all my own diagnosis. You guys know how much a nice like a Samsung fridge costs, stainless steel, top, nice one? Any idea? Take a
Like
guess.
$2,000.
Plus two, 3. Seen them for $4. I probably wouldn't go for the 4 one. They can be expensive. I found a brand new in the wrapper Samsung refrigerator for $800. And in my mind, I'm like, probably there's something wrong with it, but you know what? It's clean, it's good. Even if there's a defect, I'll figure it out. Bought it, brought it home, put the stuff in there. 4 days later, the milk is going bad. I look at the temperature, it says 34. It feels kind of warmer, but I don't really know. But the milk is going bad after like 4 or 5 days. I'm like, man, the milk should last at least a week, maybe a little more. And so I put my thermometer in there. It's actually running at about 47. So rather than 34, it's like 47, close to 50. It needs to be colder. But I look on the panel and it says it's 34. Did you ever think about how that panel knows it's 34?
Sensor.
A sensor, exactly. A sensor that's a semiconductor, and it's actually called a thermistor. And so it uses a thermistor to to tell the temperature. Well, I end up doing a little diagnosis. I put my thermometer in there and it's measuring almost 50, right? But the sensor thinks it's 34. I measure the sensor's resistance. I diagnose the sensor's no good. You know how much the sensor costs?
300.
$9.
Oh.
Meh. $9. So I got a really nice fridge, did my own diagnosis, put my own $9 sensor in there. I still have it.
So you saved yourself what?
A couple $1,000 potentially, at least $1,000. You know, so that's more what I'm saying is like, how they do the thermistor, I don't freaking really know. But how to diagnose it, I got it because my area of expertise is automotive. Thermistors, Hall effect sensors, diodes, transistors, like you need to know how to diagnose that stuff. The car's gonna come in with a thermistor issue. Matter of fact, they just had a broken thermistor. It was yesterday. It's a coolant temperature sensor. We use thermistors on automotive. I am doing an oil cooler on a Jeep 3.6 Pentastar. And that coolant temperature sensor was so tight, I tried, and I snapped it clean off. So I need a new temperature sensor. But again, well, the diagnosis on that's easy. It's in 2 pieces. But sometimes they fail where they're reading the wrong temperature, right? So how we diagnose these is how we fix cars. Cool, but this is just kind of giving you the science of it. Remember, it's introduction to electric. Cool. So again, here's your gallium arsenide. We do some stuff with that. We have our silicon carbide. We do some stuff with that. We have germanium. We will use these elements for semiconductor purposes, and exactly the details of how, I can't say. I can't say. Somebody else can say. Okay, cool. Decent on semiconductors. Mainly to understand why. Not so much the details of how, but the why. And then when we get into components, we'll talk about how to diagnose. Cool? Okay. Now, I heard your question. This right here is like a chapter objective.
Oh, okay.
That's all.
Okay.
It's just to guide more the instructor to make sure I'm hitting all the objectives.
Oh, but does it go based on the book?
Yeah.
Okay.
Exactly. So, and just for all of your information and reference, the way a class is done is it's designed by objective. At the end of this class, what should you know? And this is to help me make sure I'm hitting all the points.
Okay.
If I miss an objective, I'm kind of screwing up. In fact, if I miss an objective and accreditation comes through, they're gonna be like, hey, you didn't really hit all your objectives. And I'll be like, ooh, shoot, you know, so I'm accountable. Cool, so it's just mainly for my reference. Because when I build this out, I gotta make sure everything I'm supposed to hit's there. Okay, direct current, alternating current. Who remembers a little bit of this from last week? Direct current leaves the battery, it technically leaves the negative and goes to the positive, okay, but let's chill on that a little bit. And let's just say it goes positive to negative, even though that's kind of wrong. That's how we're gonna be looking at the diagrams. It always leaves the positive to the negative. It doesn't alternate, it doesn't switch, it just, see what I'm saying? It goes directly out of one terminal and directly into the other one. Now, we'll make it go do some stuff first. We'll make it go through some light bulbs and do some work, okay? DC looks like this. On your meter, if you were to put it on DC and try to measure an AC component, nothing's gonna register. Because it's not looking in the right way, right? But you can't, your meter just gives you a number, cool? This is actually what an oscilloscope looks like. An oscilloscope gives you a graph. So I'll describe this. See this right here? This is volts. This would be 0, 1, 2, 3 volts. This has 3 volts, and this is over time. Let's say this is 1 second right here. This would be 1 second, this would be 2, this would be 3, right? If it's 3 volts, 3 volts, 3 volts, that would just mean, oh, it's staying at 3 volts, cool? It's just 3 volts and that's it. It's direct, it's consistent. Now, if you were to see it like this, 3, 0, and 3, the graph would be very helpful because you can see what the voltage has done over time. Typically, this wouldn't be seconds, by the way. Typically, this would be like milliseconds, microseconds, nanoseconds. Like, this is usually a very short time. If you're trying to check the battery, you don't really need to graph that. Makes sense? Like, you just don't, if you check the battery and it's 12.6, cool. You don't need to see if it's changing and oscillating. However, if we were to look on AC, I'd like to point something out. This is 3 volts DC, see, flat line. This is 3 volts AC. What's happening here? It was -3. It didn't instantly go up to +3. It actually ramped up. It ramped up fairly quickly. It hit +3, and then what did it do?
Drop down.
Turn right back around and alternated itself to -3. Then it alternated itself to +3. Then it alternated itself to -3. If you put a meter on this, and you set it to AC volts, you get a reading of 3 volts. But in reality, what's actually happened, if you were to graph it with an oscilloscope, is it's gone -3, +3, -3, +3, -3, +3. Cool? That's how AC works. If you were to visualize it, remember how we had the battery, right? There's a positive here and the negative here, and in DC it all goes like this? Okay, in AC it's a little bit different. On AC, we're going to push it this way. Then we're going to switch. We're going to make this one the negative and this one the positive, and we're going to push it that way. And then guess what we're going to do? We're going to switch. Now this one's going to be a positive, that one's a negative. I'm going to push it this way. So with a DC system, the electrons flow. They leave the positive, I'm lying, they leave the positive, and they go to the negative. Boom, 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 boom. With alternating current, they start to go this way, then we turn around and make them go this way. We turn around and make them go this way. We turn around and make them go this way. It goes up, it goes down. It goes up, it goes down. Does that kind of make sense?
You wanna know a way to simplify it?
Shoot it.
DC is a chainsaw, AC is a bandsaw.
I don't know what it
Go
is.
back and forth.
All right, so how about more like a sawzall? Like a
Yeah.
Okay, gotcha. Okay. That's pretty hillbilly, but I like it. I like it.
That's the person from the Chesapeake to do, to say that.
Think of the area we're in. It makes more
Uh-huh.
sense.
I could sing a song, but about West Virginia?
No.
Okay,
Maryland.
moving on. All right, DC,
Wrong state.
straight through, right? AC, alternating up and down. If, let's say, you wanted to see this in action, we could get an oscilloscope and we could hook this up to the wall outlet and you would see this alternating current occurring. One more thing I'd like to point out is the number of oscillations in a second is the hertz. So that's the frequency. How frequently does it alternate back and forth? Does anyone have any idea what the standard is for a US household? It's 120 volts. Sometimes we call it 110.
So the current, for the current
Sure.
goes up and down, not back and forth? Because right now you mentioned back and forth. So like for AC, the current should be going up and down, right?
I'm gonna re-explain it one more time. I
Okay.
got you. Anybody know what the frequency is in the US? 60 hertz. So when you buy an appliance for the US, it's designed to be 120 volts. By the way, that could be like 115, 110, right around there. And it needs to alternate 60 times per second, 60 hertz. Cool. Then the appliance will be happy. Now we had some power outages. Anybody run off a generator? You ever notice sometimes the stuff doesn't work quite right? Like if you try to turn the microwave on, it'll be like, that's because your generator probably can't keep a clean 60 hertz cycles, right? So the power grid's really powerful and it'll be like 60, 59, maybe 61, probably right at 60 hertz. And your appliances are like, I was made for this. Then the power goes out, you hook up the generator and the generator's like, I got this. And then you run too many loads and it's all of a sudden like, 55, 54, 53, I'm only 53 hertz. You will hear that in your appliances, make sense? So when it's AC, we alternate it. This is voltage. Cool? So if it's a house, we're not going to 3 volts, buddy. We're going to like 120. We're going to send it way up there. That's why I give you a little zap. It's voltage, electrical pressure. House has 120 volts of electrical pressure. That's enough to go like that's how I lost my hair. I had a full head of hair and then I touched that thing and all of a sudden poof, it was gone. Okay? Now in a battery, it's just whatever the voltage is. They could make a battery that's 120 volts. I don't know of Well, there are batteries that are similar to that, but it's just a little bit different, right? It's solid, it doesn't have to, there's no frequency, there's no alternating, there's nothing. So voltage is up and down, that's the pressure. When we talked about, like Priscilla, what you were asking, the voltage is the amount of pressure. That's a little bit different than the flow. So like this doesn't show flow. This just shows pressure. We're increasing the pressure, we're reversing the pressure, we're positive pressure, negative pressure. The amount of current flow isn't shown on this graph. The amount of current flow, if we wanted to know that, does anybody remember the type of measurement that we would use to measure current flow? Amps, exactly. So this is showing voltage. If you want to see current flow, you need to use a different tool. You don't need a voltmeter, you need an ammeter. The multimeter can do both. We change it over to amps, and then you probably see, I don't exactly know what the amperage would do. It would kind of depend on the demand and that type of stuff. Now, for a visual, what I want you to picture when you see this, in DC, the electrons are leaving the positive and going to the negative. With AC, that electron is physically moving from, let's say it's these lights above us. Your electrical panel is pushing the electron and then pulling the electron and pushing it and pulling it. So I visualize that kind of like side to side, but in reality it's along a strand of wire. Let me see if I got wire right here. I got a bunch of wires, but I don't know if I have the exact wire I want. Okay, here is a wire. With this wire on AC, the electron is literally going down, up, or left, right, left. The electrons physically move, you understand? The current flow is more the quantity of the electrons moving, right? So if it's AC, we know some amount of electrons are doing this, and this, and this, and this. Make sense? So when you want to measure that, we got to actually put it on amps, so we got to measure it, and it'll give us a number. Like this probably won't move that many amps, but let's just say it was 5 amps. There would be 5 amps, and I forget how many that was, but it's the same, whether it's AC or DC. It's a certain, how many, do you guys remember how many electrons it was? It was like billion or trillion.
5 or 6 billion.
6 billion.
There you go. So let's just say 6 billion. 1 amp would mean 6 billion electrons have gone that way, and then 6 billion electrons have gone this way. 6 billion have gone that way, 6 billion have gone this way. Now, if it were a DC wire and you had 1 amp, that would mean 6 billion in 1 second, I believe. That would mean 6 billion electrons went right by you in 1 second. Cool. So it's a hard thing to understand, but AC, the main takeaway, alternates. Oops, I threw this up here and I changed the screen, didn't I? AC is alternating the pressure. So it's pushing and then it's pulling. And it's pushing and it's pulling. How many? Depends on the amps. Cool? If it's 1 amp, 6 billion within 1 second, apparently. It's pushing 6 billion, and then a second later, it's pulling 6 billion. If it's DC, it's pushing 6 billion in 1 second, that's it. They don't come back. They go directly to the other terminal. Cool? It's kind of different. All right, now in automotive, 99% of what we do is right here. DC, have a nice day. The few things we will use AC. Some sensors. Sensors sometimes we use will be AC. Additionally, if you have a car with like a power supply that you can charge your laptop, like if your car has one of these, like a power outlet like this, you may actually have to measure AC at that to see if it works. But that'd be pretty rare, right? Maybe some sensors and maybe some power outlet, not much.
That's why they sell those like converter things, right?
That's what it does. The converter takes DC like this. Your battery's 12.6 volts or so, right? And it makes it into this. It should make it into 110 volts at 60 hertz. How many amps? Probably not a lot. Probably not much. But enough to maybe charge. You're not going to run a microwave in there. Microwaves pull a lot of amps, believe it or not. Like 15, 12,
Yeah, it's a nuclear bomb inside a box.
That's
No,
how I lost my hair.
nuke.
That's how I lost my hair. Okay, kind of makes sense? Now, there's a big thing coming up with AC though that's important. A lot of electric vehicles are going to AC motors. Why? It takes a little bit of time to explain, but when you wanna, we want these cars to be fast. We also want to be able to pull a lot of weight. We also want to be able to do a lot of cool stuff. AC makes sense. When you can go to a 3-phase AC, you can get a really smooth, very powerful motor. So we're changing from, we'll take the battery, right? We'll take the battery with DC, we'll send it to the inverter. The inverter will invert it or convert it to AC, and then AC will run the motor. Make sense? The electric motor. But it goes the other way around. Nobody in here's got an EV, do you? But has anybody ever plugged an EV in to charge it? Because you're going to do that as part of this class just for fun. I'm going to make you do it. Then you'll be accepted into the club. Okay, when you want to charge your car, we plug the charger into the AC outlet, and typically they're going to run on 240, right? So we're going to have something like this. We're going to have, it gets a little more complex. We're kind of going to have two of these. There's going to be a 120 and another 120, and that's going to make your 240. Sometimes we call it 220, right? It's going to take that AC, and it's going to go into the car, and it's going to go through the onboard charger, and that's going to convert it to DC to the battery. So with hybrid and EV stuff, it's going back and forth all the time. We charge it with AC and put in the battery, which only takes DC, but then when we drive, we're taking it from DC, and a lot of times we're making it an AC because we have the AC drive mode, traction motors, or motors that make the car go. Make sense? So the AC and the DC and the AC and the DC, it's all over hybrid electric vehicles. A lot. Cool? All right, now from there, let's say the AC continuously changes its direction of current flow and the alternating voltage repeatedly reverses. That was that picture, right? AC is produced in a sine wave. What is a sine wave? This is a sine wave. If you hear the term sine wave, it's this ups and downs. It's sort of like
Roller coaster.
mountains and valleys. Yeah, it'd be like a cool roller coaster game, like.
That's a boring roller coaster, just
Whee!
up and down.
I think that'd be a great roller coaster.
Depends on
Over
the route.
and over and over. This is a sine wave. Okay, so AC just is on a sine wave. If you have to diagnose an AC problem, your meter is probably not going to cut it. Your meter is going to give you a number, right? Your meter is going to say 3 volts AC, and you'll be like, I don't know if that's good or bad. You may have to go get the oscilloscope and be like, let me see the sine wave. Let me interpret what we call the waveform. You may see good, and then you may see one that's flat. And then you might see some issues, right? The sine wave can tell you more about the diagnosis. Do you understand what the sine wave is? All it is a measurement of voltage on the up and down and time on the left and right, right? So this is just time. Cool? By the way, you could calculate the hertz too. You could calculate the frequency. If you were to count, we start at the low, right? So this is 1 cycle, 2 cycles. You'd count 60 and you'd have to see in 1 second there better be 60 of those suckers. If there's not, you got an issue. There's another way that you can measure that though. You can use your meter and you can put it on hertz, and hertz will just spit the number out for you. It'll be like 59 hertz, and you're like, oh, okay. Kind of makes sense a little bit, just as a theory.
Which setting is that?
You're gonna have to put it on AC, and then you might have to dig around and look for hertz. If it has it, a lot of meters won't. The Fluke probably does. Cool. And then, like I was saying, hertz is the measurement of frequency and indicates the number of cycles per second. 60 hertz means 60 times per second. Okay, and then frequency describes how rapidly AC current reverses polarity. Amplitude describes how high the voltage level goes. Who remembers this last screen where AC was right here? What was the amplitude?
3.
3, exactly. Boom. Two slides. 3 volts is the amplitude. Generally, we won't call it amplitude because we know it's measuring volts, and we'll just be like, it's 3 volts. But like technically, if somebody said, what's the amplitude? And you're like, amplitude? That just means how high, which should also likely mean how low. Makes sense. But it's mostly focused on how high. Cool. And then, here's what's kind of interesting too. Every car, all right, not exactly every car. It's always hard to say every and always. Almost every car, unless it's really old or unless it's a hybrid or an EV, almost every car uses AC to create a current flow, which then gets converted to DC, and that's how your battery charges. You guys have heard of an alternator?
Yes.
Your alternator creates a three-phase AC waveform, and then we send it through a diode rectifier bridge, several diodes, and the diodes will basically cut the tops off or cut the bottoms off, and that's how it rectifies it into DC. So your alternator makes AC. The reason we don't go real in detail with that is you don't really measure the AC part, you just measure the DC part. If the DC part isn't working, you make sure the alternator has what it needs. And if it has what it needs and it doesn't work, it's like that crappy employee. What do you do if that employee has everything it needs and it doesn't work?
Fire.
Exactly. You get a new alternator. Technically though, if you wanted to be in detail and you could access the points and you took the alternator apart, you could actually measure the AC alternating current inside the alternator. We just really don't. There is one test we'll do. The AC is made into DC using diodes. We'll do a diode test, and that's something that we're going to do in charging systems. So when we get into charging systems, which is much after the midterm, you'll be like, why are we doing AC? Oh yeah, I kind of remember AC. We take the AC, we run it through a diode bridge, and we make it into DC. Cool, we're going to do that test. It's like one button on the battery tester. You guys have used the battery tester, and it's like, charging system test. It's doing that for you. So those battery and starting charging system testers have allowed the technician to get kind of stupid. Like you don't even have to know. It just says charging system test pass. And you're like, okay, cool. But I want you to know a little more than that. It does start with AC and rectify it to DC. And a problem on the AC side will become a problem on the DC side. And the diagnosis is not really that hard. Cool. And then AC is used in electric motors on most hybrid vehicles. That's what I was saying. The inverter is the one that switches it DC to AC and AC to DC. This thing's a workhorse. This is a beast in those cars. This does a lot of work. Anybody got solar at home? You got an inverter. I'll tell you right now. Your solar panels make DC. DC don't power your house. AC power your house. So we use the inverter. The inverter takes all your DC from your solar panels, and by the way, battery too if you have battery backup, and then it makes it into 240 volts at 60 hertz AC, and your house is like, I like this, I'm happy. And if it produces too much, it sends it back to the grid, and the grid's like, cool, this works for us. But if your inverter was messed up, because all the electrons have to flow through the inverter, so a lot of them. That's why it has big heat sinks and fans and stuff. And ideally, if you can keep it like on the north side of the house where it's shady or inside, even better, right? But if your inverter was kind of funky and it wasn't able to make the clean 240 volts and the 60 hertz and stuff, it'll protect itself. It's not gonna go into a mode where it's gonna ruin your appliances. Makes sense? And inverters fail, and they're expensive, a few $1,000s, maybe $5,000 for a nice one. Cool. And then how they work. Okay, we're back to solid state electronics again and semiconductors. But most inverters use a semiconductor device called an insulated gate bipolar transistor. Can you guys remember those words? Insulated gate bipolar transistor. No. IGBT. So IGBT, no, not L. This is IGBT. Insulated gate bipolar transistor. If you are dealing with hybrid EV, they'll be like, oh yeah, the inverter. Mostly the main thing that's in the inverter is these IGBTs. These have got to be like the strongest transistors you've ever heard of. So the IGBTs, they cycle the DC current polarity forward and backwards, mimicking the AC voltage sine wave and powering the traction motors in the driveline. Hold up. Now I just told you, if you have a DC like this is pretty easy to make. If you want it to be able to power, let's just say, we got into a technology that's currently emerging. It's called V2G or V2H. Anybody ever heard of it? Vehicle to grid, vehicle to home. Let's say you got an EV, even though you hate them, or better yet, I'll meet you halfway. Let's say you got a Ford F-150 hybrid.
No.
With the standby with the home. Wait, I'm gonna help you. With the standby, the home generator. I can't remember what they call it. It's the one that comes with the generator. It's not a power station generator. That's GM's. Whatever it is, that truck right there. If you were to put it in the mode where the truck will act as a generator, the engine will sit there and idle. The V6 will sit there and idle. It'll run its generator, traction motor type thing that's in the bell housing, and that inverter has the ability to take your DC out of your out of your big battery in the truck. It's a hybrid. It's got a high voltage battery, and it will actually use the IGBTs to mimic a sine wave at 60 hertz at 240 volts, and that F-150 will power your house when the power's out.
Yay.
Okay, now you're giving a little bit more. Not only they get a little bit better fuel economy, but they can actually also literally have the ability to power your house. How does it do it from DC though? It has to have DC going to these IGBTs, and the IGBTs have to be switching back and forth to make this sine wave. If it can make this sine wave, all your appliances are like, hey, I know that language. 60 hertz? Oh yeah, I'll turn on. Ding, things are on, your fridge is on, your microwave is on, all your stuff is on, and the truck's just out there idling. I mean, you gotta admit, that's kind of cool.
Yeah.
Now
Kinda cool until it gets
Raptors,
stolen.
oh no, you can lock the truck all up. You can lock the truck and leave it sitting there idling.
And then you can unlock it.
Don't do it in the garage. You can't leave the truck running in the garage. Put you to sleep.
Bad things.
What with the garage
I'll
open?
put my 75 in it.
That's what I would
and
do.
then
That's what I'm
garage.
saying. If you could nose it in and have the exhaust mostly going out the garage, or better yet, leave it in the driveway and run a bigger, fatter extension cord from there that does
Better
240.
yet, just put that hose from the.
You can do it. Get the exhaust hose.
Bam, put it inside.
That's what I'm saying. In that way, that's pretty cool. How does it do it though? I just want you to understand it was the IGBTs. The IGBTs can basically, as it says, mimic the AC voltage. But that's what it does. It makes the AC voltage look like it's coming from the grid, and your appliances are chilling. They're like, I'll run on that. That's perfect. That looks just like the grid. Your generators do the same thing. Actually, that's not totally true. Your generators will run a generator at a correct frequency to make it. The generator actually makes that AC sine wave, whereas an inverter takes the DC and it mimics it. They should look the same to the appliances though. Kind of weird, huh?
So you're telling me it's transistors bipolar?
It's a insulated gate bipolar, yeah, and it's a transistor too. So if you look at that, they're designed to work with either AC or DC. AC converts DC to a transformer rectifier. Generally, transformers step up or step down voltage. So if you have 110 and you want 12, transformer steps it down to 12. If you have 12 and you want 110, a transformer steps it up. Makes sense? A transformer transforms. It steps it up or it steps it down. The big power lines come in, they go to a transformer, and that steps it down to the 110 or the 220 or 240 that your house likes. You can't be running your house off of kilovolts. It's gonna stuff, right? So transformers are used all over electronics. Rectifiers are slightly different. A rectifier is generally something that will take like AC and make it into DC, which is not all that hard to do, but that's what a rectifier does. And then generally when we are working with these, we call them inverters. So rectify means kind of like to stand up. If you have AC, remember it goes positive to negative. Well, DC is all positive. It doesn't cycle. So if you want to rectify it, you bring it all up positive. That's what a rectifier does. Generally, we'll use inverters to that. Or it could even be the other way. Technically, a rectifier is AC to DC, and technically a DC to AC is an inverter, but really we call them both inverters. If you go to buy something that makes AC to DC, they're gonna call it an inverter, even though from a pure standpoint, it's a rectifier. Cool. And this one's gonna mostly go over your head, but I'll shoot it anyway. The number of separate staggered power windings in the motor alternator is called a phase. Just gonna walk away with that. Now, I'll give you a little bit more, okay? On this one, this is a hybrid, or it could be EV. We're gonna send high voltage battery. This is DC. The DC is gonna use these things. What do you think these are?
AC?
These individual things is what we were just talking about. These take your DC and they're gonna invert it to that sine wave and make it AC. So what do we call these?
Transformers?
Close.
Inverters, IGTBs.
Bingo, IGBTs.
IGBT.
Insulated gate bipolar transistors, IGBT. Wow, that's a mouthful there. Okay, here's your IGBTs. These are the main workhorses, cool? Your battery, DC comes in, this makes the AC, but I want to point something out. There's one set, there's two sets, there's three sets. There's three sets of these because it's going to make 3 phases of AC. Now, I won't go totally nuts on this, but 3-phase AC is something you got to be a tiny little bit familiar with, because this isn't just going to run on one AC winding. If you look at these, look, orange goes to 1, 2, red goes to 1, 2, blue goes to 1, 2. This is 3 phases, means there's basically 3 individual circuits powering that motor. Now you see why 3-phase AC is cool. Rather than having like 1 piston pumping, you get 3. Makes sense? That's why 3-phase is beautiful, because if we were to look at 3-phase, I didn't plan to go super in detail, but I'm actually going to give you a little bonus right here. Because I'm feeling it. Alright, if we look at these colors, this blue one, let's just say we focus on the blue. It was positive, it was negative, it was positive, right? What's kind of crazy is if we added another one that was black, this was like neutral, this is 0, then it goes positive, negative, and it's starting to go positive. Let's just say we add another one in red, it started negative, it goes positive, it goes negative. This basically will make sure that that motor constantly has, at least like at this point, this one is pushing, and this one is pulling. It makes it really smooth operation. You got these two pushing and this one pulling. Pick a random spot right here. Look at this spot. Black is pushing, blue and red are pulling. Let's look at this spot. Black and red are pushing, blue is pulling, right? So you got 3 working at the same time. The 3 phases make everything really nice and smooth. You can have 3 working toward moving that motor at one point. You see how you can make more power there? 3-phase is kind of like the go-to with these hybrids and EVs. So when you hear phases, it's just like this. One of these is just an AC waveform. Blue, cool. But we've added 2 more. That's why it's a 3-phase. You got something, huh?
Does that technically increase the hertz then? Because it increases the frequency? Is
Okay.
that pretty much what it's doing?
I'll clarify that. You guys get the question? Doesn't that make the hertz more? The way we measure the hertz on the 3-phase AC is individually. So we're just measuring this one. If this one's at 60 hertz, it's still 60 hertz. But this one's at 60 hertz, and this one's at 60 hertz, and this one's at 60 hertz. They don't combine. What it'll do, if you look at it, if I jump back to the presentation, it's saying, let's say, because there's 3 individual ones, we need to space these out equally. Do you see how they're spaced equally? That means that at any given, like let's say we were to look at that previous page, blue and red are pushing, black is pulling. Or red and black are pushing and blue is pulling. We need to space them equally. So back at this picture, it was going to show these are offset by 120 degrees. You're like, what the hell? Anybody ever done snowboarding or skateboarding? What happens when you do one full turn? How many degrees is that?
120.
I heard a few different numbers.
360.
That was a 360. How many, let me think about this. How would I explain this best? In one revolution, being a 360, if we wanted to fit 3 parts into there, how big would the parts be? Exactly. Now do you see why it's spaced on 120s? In one revolution, we have room for the 3 phases. So if we space them out perfectly, every 120 degrees, right? Like here you are, you ready? You turn 120, that would be a phase. You turn 120, that would be a phase. You turn 120, that would be a phase. So they're spaced on 120, so they're equally spaced. So we constantly have, it's coming into like either 2 pushing, 1 pulling, or 2 pulling and 1 pushing. So we space them out. If this one's at 60 hertz, we're going to just move the next one forward 120 degrees of rotation. Make sense? You're visualizing it left to right. What that looks like in the motor of the generator is like that, right there. Okay? Without even going on the big screen, right? So from red to blue is 120. From blue to orange is 120. From orange to red is 120. So these are spaced on 120s so that they're equally. If this one's 60 hertz, blue is 60 hertz, red is 60 hertz, orange is 60 hertz, they're all still 60 hertz, but they're timed a little bit different. Some are coming in a little early, some are coming in a little bit late. How much? Well, this one's at 0, this one's at 120. What's the next one? 240. Oh, I didn't know it was locked.
No, poor Mason.
Okay, so 0, 120, 240, all spaced out at 120 degrees. And then when we really get into the hybrid stuff, if you really must know, they don't always operate on 60 hertz. We can control a lot of stuff by varying the frequency, including regenerative braking. Okay, cool? I think that's as much as we'll do on the 3-phase of AC, but just kind of like a little bonus. If you hear the term 3-phase AC, that's how it's working. Okay? And then as you guys can see, we talk a lot about the chassis ground. Remember this? The chassis ground goes to the negative terminal of the battery. So if the electrons leave the positive and they go do some stuff, they probably end up in the frame. And they go down the frame and they go to the strap and they end up returning to the negative all the time. Part of the reason this is shown on this screen is because when you have 3-phase AC, there is no ground. It doesn't need a ground. We might put a ground in there for safety, by the way, but now can you guys visualize why in AC we don't need a ground? Remember we talked about that in the plug? We'll have, if one of these is positive, one of them is negative. We don't need a ground because one's positive, one's negative, so that's how it will work. It's kind of crazy, huh? Remember, the current's alternating, so it's kind of interesting. Cool? Okay, and then we talked a little about it. They're more output, they're smoother. A lot of times we may use sensors that will use AC, but you know, we'll get into those a little bit more later. And then let's say a varying signal is an indication of changes within the system being monitored. What that really means is let's say it's a speed sensor. If something speeds up, it creates a varying signal. If something slows down, it creates a different signal, right? So the signal can indicate speed or position. Remember we mentioned the Hall effect a little bit. If there's a tooth right there, it'll say, oh yeah, the tooth is there. And then if the tooth leaves, it'll say, oh yeah, the tooth isn't there. Just saying, the varying signal is an indication of a change. What's the change? Depends on the system. Maybe it's the change in wheel speed. Maybe it's the change in door handle position. Make sense? So now do you understand, if you're a computer, you need to know these things. The computer needs to know what's the wheel speed. The computer needs to know what's the door handle position. Do you agree? We can use
to know if the door is slightly ajar.
exactly, and we use sensors. Sometimes switches. Okay, switches are old school. Sensors are a little more new school, right? Sensors are solid state. Switches are like this. Okay, those switches tend to wear out. Sensors, at least in theory, should be more reliable. So we use sensors to tell is the door ajar, is the door not ajar. We use sensors to tell is the wheel's turning, is it not turning. We use sensors to tell whatever. You tell me, whatever it is. Cool. All right, and then again, we talked a lot about power and ground. All right, so I want to clarify this a bit more. The supply side is the positive side of the circuit, and the return side is the negative. And this is where we break from electron theory. Okay, remember I told you we were going to? Technically, the ground is the excess of electrons, so that they're really leaving the ground and going to the positive, okay? I'm telling you the truth because I want you to know. However, we're leaving that behind right now, and I don't really want to bring it up ever again. Are we good? Because all the wiring diagrams and everything is drawn as if it's positive and negative, and it doesn't really matter. To be honest, it doesn't matter. The way we measure it's the same, it doesn't matter. Cool. So the supply side is the positive, good. And the return side is the ground. So if we're to jump back on that chassis ground looking thing, we will leave, that's amazing, that red really won't show up on the projector. You can kind of see it, but it's not worth being totally in the dark. All right, so this is red. Electrons leave here. They do something, and they might return via the chassis or a wire, whatever, but ultimately, all the electrons will end up there, okay? That's really what we're trying to say right here. So when we get into that, because the positive side is where it starts, we can call that the source. The source of the power, if you will, is the positive side. So if I say, what's the source voltage? You know what that means? Last week we measured the source voltage of that board. Do you remember? What did it read? I think it read about 12, huh? So that is source voltage. If you want to know what voltage you're looking for, you generally would start with measuring the source. Measure the positive and negative. If it's 12.6, that's your source voltage. If you turn your headlight on and it doesn't work and you want to measure the voltage at the headlight, about how much should you have available at the headlight? Yeah, exactly. So you always want to start with the source. Now, if you're working on something weird, like tractor trailers run 24 volts. So if a tractor trailer runs 24 volts and you're down there checking voltage at the headlight and it's getting 12, you think it's good. No, you didn't really measure the source. You need to know what the source is. Make sense? Pretty much everything we're going to work on is going to be 12 something. Cool, but that's how you check the source. The source is how much positive voltage is available at the positive terminal of the battery. What if you had a battery that was kind of discharged and it was reading 6 volts? Are you expecting to have 12 volts available at the connector and the headlight? The source isn't even 12. You can't get 12 if the source is 6. Cool? So for your reference. Okay. Power or feed side of a circuit refers to the wires and components that originate the positive terminal of the post. You know what that means? That's the positive side. All right, that's the positive side, or the power feed side. Now when we get a little bit more into there, it's going to be important that you know ground side. Ground indicates the portion of the circuit that returns current flow to the negative side of the battery. So the ground is going to be the chassis ground. Remember that picture? If you don't, I'm going to bring you there. Remember, this is the negative terminal. We run a cable to the ground. This is the chassis ground, the frame ground. All the metal stuff that's bolted to the frame and chassis and the unibody, that's all chassis ground. And that's all going to end up at the negative terminal. So that's the ground side. Overall, that's what ground is. Make sense? It doesn't have really anything to do with what you walk on. It actually probably really shouldn't be called ground, to be honest with you. Some manufacturers, sometimes they'll call this the common. Common? What's common about it? Well, I'm glad you asked.
That's on every vehicle.
Close. If we power the headlights, if we power the locks, if we power the radio, there's 3 different supply sources, right? There's 3 different supplies. It's all coming from the battery, but it's all, we send a wire to the radio, we send a wire to the headlights, and we send a wire to the power locks. Cool? They all share the same ground. They have the ground in common. They all use the chassis for the ground. That's why they'll say common sometimes. What's kind of cool, like on a lot of cars, the ground will typically be a black wire. So if you look at a headlight and you're like, oh, there's this color wire, whatever, pick a color, name a color.
Blue.
Pink wire and a black wire, the black wire gonna be the ground. Make sense? If it's a Toyota, you know what the ground color is?
The solid. No, the one with the line.
It's white with a black line.
Uh-huh.
Exactly.
Well, like, cause you know, like for example, like speakers, they have like a solid color,
Uh-huh.
and then
Yeah.
the one with like white with the color, the same color.
Sure.
That one's the negative, right?
That's for your, well, in speakers a lot of times,
Usually positive solid, right?
you can do it however you want, because when you're wiring a speaker, you connect it to the receiver and you connect it to the speaker, so whatever, you just gotta be consistent. Red over here needs to be red over here, so if you make the solid go to red, you want the solid to go to red, but technically.
But like in like the wire harness, like the
From
main
factory?
harness,
From
the factory
factory?
harness,
Typically.
usually the solid is like positive, right?
Typically, but.
Because I know,
that's-
like for example, left front is always a different color than right front.
Yeah.
They're like
Yeah, they
different
have
colors.
to be.
Yeah.
Exactly. And it can vary though, so I don't want to totally, I don't
Okay.
want you to nail me down on what it always is.
Okay.
But commonly, yes.
Okay.
And commonly, being the joke, if it's a ground, it'll a lot of times have a common color, right? So like on some vehicles, actually green is ground, and it's common with all these different things. If you see a green wire, you know it's ground. That's why they'll sometimes call it common. Cool. So the ground is a lot of times gonna be the same color, but not always, but a lot of times. And sometimes you'll even see like a whole bunch of these grounds coming together and being bolted to the chassis, and that's how they're grounded. They don't all have to run all the way back to the battery. They can run to a frame or chassis and then be grounded through the actual metal. It was a good idea. It saves a lot on wiring. But as a fun fact, if it was like a fiberglass boat, the boat's made of fiberglass, you can't ground it. You actually have to run a positive and a negative to every light if it's a fiberglass something, like a boat or something. Cool. And then like that's what we're saying. The ground side starts at the negative terminal and it goes to the frame, to the chassis, to whatever. So if you visualize it, stuff leaves the battery, goes to the positive side, and then all somehow makes it back to the negative terminal, but probably through some metal stuff. And that's pretty much what this means, which means most of the metal components on the vehicle are grounded. So if you're trying to do the meter and you need a good ground, probably finding something shiny metal will work. But if that piece of shiny metal is a screw that's threaded into plastic, that ain't grounded, no matter how shiny the screw be, because it's not going to the chassis, it's not going to the whole grounded chassis and body, right? It's just floating in plastic in the dashboard.
But the screw goes in the dark.
It might, if it's radioactive. Sure. All right, so here's that picture again. It's going positive, it's doing some stuff, and it's gonna make it negative. Keep in mind, because we share this ground with all the stuff, if the car has some weird electrical problems, you may really need to consider looking at that ground connection. If you have a bad chassis ground connection, you can have problems in all aspects of the vehicle, all sorts of stuff, see, because they're in common. Makes sense? So that's another thing to consider. Rust and corrosion will increase the resistance and the heat, which will lower the amount of current that can pass through. We talked about Ohm's law a little bit, right? We're going to talk about Ohm's law more. But if you have increased resistance, whether it's on the ground or the positive, by the way, that'll decrease your amps, that'll make your bulb dim, that'll make your motor low speed and weak, that'll make, your magnetic field not be strong, depending on what the load is doing for you in that system, depending on what the workhorse is. It's not going to work as well, so we want to keep that in mind. And then many computer circuits use a dedicated ground wire from their sensors back to the ECM or back to the computer. The reason for that is, we got a lot of different things happening on these grounds. When it's a sensor, it's very, very sensitive to voltage changes, to resistance, to corrosion and stuff. So rather than rely on the chassis, we'll actually send a ground wire out to the sensor. That way the sensor's got its own dedicated clean ground. It's like, hey, we don't want you hearing all this noise on these other circuits. We want you to be reading accurate and smooth and clean. That makes sense? So we can do that too. We can send extra ground. Even though it might not need it, we call that something, it's called redundant. It's called redundant. It's called redundant. Do you understand redundant? I said it once. I didn't really need to say it the other 2 times, but in case there was something wrong with the first time, I gave it to you again. I gave it to you again. Makes sense? It's like, hey, we don't really need it. It's redundant.
Thank you for the redundancy.
Yes, you got me. I'm redundant. See, now you understand redundant. I like it. Cool. And then talking about the measurements a little bit. Continuity is achieved when an electrical circuit has a continuous and uninterrupted electrical connection and is capable of conducting current. That's exactly how I describe
That's a lot
it.
of words.
That's a lot of word. You know what I like? Continuity means it's got a clear path. It's got a continuous, if you want. It's continuity. There's continuity there. If you worked shift work, the whole song about that. About like 7 to 3 and 3 to 11, and then the really bad one that I worked for a while was 11 to 7, 11 p.m. to 7 a.m. Not a lot of fun. What they would do a lot of times is when I was done working at 7, they'd have me stay a little bit and just kind of tell the first shift guys who were coming in to get started what was going on. You know why? They wanted continuity through that. I was supposed to like leave, or they call it a turnover. I'd leave a turnover what I was doing. If I was doing a big job and I like tightened 10 bolts, but there was another 10 to be tightened, they'd have me write up, hey, these 10 are done, these 10 are not done. So there was continuity, there was an understanding. It's a continuous communication. That's continuity. It's a good way to look at continuity. Whereas if I were just to be like, well, my shift's over, I'm out, they'd show up and be like, man, what the heck was going on here? Well, it looks like it's done. That would be bad. That would not be continuity. There's no continuity there. Cool? Pretty simple. How can we measure it? Multimeter. Set to measure ohms, connected between 2 points. Now I'll tell you something silly, and I'm telling you, if you end up like this, I'll deny ever knowing you. On the internet, I post these to the internet. Okay, just because I'll repurpose them, but also you benefit from them. And some people, it's hard for them to get. You guys are paying like next to nothing. In some areas, people can't really get this type of education. Cool. So I share some of it. I may take it down. I can take it down whenever I want. It's mine. However, a lot of times I won't call it continuity because when I go to measure continuity, what do I put it on? What do I put the meter on? Ohms. So a lot of times I'll be like, check the resistance of that wire. And I explained that, like, check the resistance of this wire, it should be 0. And the guy's like, remember I mentioned this? You're not checking resistance, you're checking continuity. And like, it turned into this whole big debate. So this is what I did. I offered him a refund. You know what he paid?
0.
Bingo, so I offered him 0 back. All right, with that being said, continuity is one term. You can call it continuity, I'm cool with that. But if somebody says measure the resistance of that wire, there's nothing wrong with that. You're measuring resistance. Low resistance means good continuity. No continuity means high resistance. Cool, that it's like I said the other day, it's the opposite side of the same coin. How do you want to describe it? I don't care, whatever you want. If there's a coin and I flip it and it's not heads, what is it?
Tails.
Okay, so
continuity
could I say
means
it's not
resistance?
heads and have you know it's tails? Sure. Could I say it's tails and have you know it's tails? Like, yeah, it's the same thing. See what I'm saying?
So you said the continuity. Wait, I cannot pronounce it. Wait, sorry.
Try
You said that means resistance, right? Or wait.
Good continuity
okay, good.
means low resistance.
Oh, okay.
Bad
okay.
continuity means high resistance. Exactly. Right, so if I say, hey, that wire's got high resistance, you could be like, oh, that means it doesn't have good continuity. That's fine. I'm chilling. But I just want you to know both angles of it. That's what I want. Cool. Right? If there's a lot of resistance, is there a good continuous path for the electrons? Right? If there's a lot of resistance, you tell me. Remember last time we talked about that fire hose, how it was kinked? That kink in the fire hose would stop the continuity of water flow.
But a lot of resistance isn't necessarily bad, right?
It depends on how it's designed. In a wire, we should never have high resistance. Yeah, exactly. In a sensor, we may need high resistance. We should have high resistance. Homeboy's knocked out. He's looking at the stars. Okay, so let's just say if you were to check that fire hose and it was totally kinked, you have no continuity. Right? Tons of resistance.
Bad resistance.
Bingo. If I say that wire has a lot of resistance, it doesn't have good continuity. You got me now. Cool. And then kind of a good way to look at it. Continuity testing determines whether a wire or component is open or whether it's two circuits are shorted. So if you put on continuity, the nice thing about a continuity test is it beeps. Right, so if I measure that wire, like here, I'll measure this wire right here. If I put my positive lead right here, and I put my negative right here, if it's on resistance, I gotta look at the screen and it says 0.2 ohms. And I'm like, oh yeah, that wire is good. It doesn't have a lot of resistance. That's cool. But if I put the meter on continuity test and I put the positive here, you know what happens when I touch the negative here?
They'll stop it.
Beep, beep, beep. Oh, that's got continuity. It's just like, it's the same. One beeps though, the beep is kind of nice. So I'm cool with the continuity test, I like it.
Wait.
Yeah?
But I thought you
Turn.
were testing resistance.
Sure. I'm testing for low resistance, which equals good continuity. Oh yeah. Okay, I see a lot of notes getting fired off in there. Remember, you'll have recording of this too.
Oh, okay, sorry.
But you can write as much as you want. People learn by writing. So even for people on YouTube, if you're struggling, like watch the video and write it out.
Okay.
I don't learn that way actually. Do you guys know how you learn? You need to know.
I actually learn better like on hands. Then
That's
like right
wrong.
now, I can guarantee you, if I walk out right now, I'm not gonna even know what I wrote or what I heard. But like when
But you
I'm
could
seeing
always
things like
reread
in
it.
person, like
So
I know
here's,
that's when I
here's my
learn.
recommendation for that. If you wrote it and you kind of forget it, sometimes going back over it, like I told, I don't remember who I told this, but you ever seen a cow in the, well, probably not. You ever seen a cow in the morning? It goes out in the morning, it gets a bunch of grain, like eats a bunch of stuff, and then in the afternoon it goes and sits under the tree and you just see it doing this. You ever notice that?
Yeah.
It's called chewing the cud. So that's a good learning method. When you get the information and you write it down or you rethink it, or in this case, that's why I make the videos. I want you to rewatch them. Rethink about it. Rethink about it. Bring it back up. Pull that grain, whatever, grass, alfalfa, out of your stomach and like re-chew it. Re-chew it. I personally wouldn't, but it does help you redigest it.
What I try to do, since that's the type of way I learn, so like I'll go like on my free time, I'll go over like certain note points
Yeah,
I have,
yeah.
and then I'll look up YouTube videos of people actually doing it,
Yeah, it makes tons
and
of
that's how I'll be able to like
Yeah.
kind of learn it.
all good. That's common. I actually learn best just listening. Like
Okay.
when I read it, I kind of struggle. But if somebody says it and I can listen and like be picturing it in my mind, everybody's a little bit different. That's normal. But your way makes a lot of sense. That's common. I think that's probably the most common. All right, cool. So like for example, right here we're measuring 1.4 ohms, and this is actually a blower resistor. So we're actually sending a little bit of electricity from the meter down through this resistor and seeing how hard it is to get back, and it's 1.4 ohms. It's not really a continuity test. It shouldn't exactly have perfect continuity because we're going through a resistor. The resistor should have resistance. That's one measurement of resistance there. Cool. Now here's a description for you. An open describes a circuit that does not have a complete circuit and therefore cannot conduct current. Okay, does that kind of make sense? Open can be used to describe a fault, has infinite resistance. A multimeter or test lamp can be used to test for an open circuit. So we're gonna spend a whole bunch of time on this, but I'll give you just like a little bit of a preview. If I have another wire, I might actually cut it, but let's just say I cut this wire. It's in two pieces. You know that's an open, right? It's an open circuit. The problem is when wires get cut on cars, you can't always see them. Especially when the mice get in the deep, dark crevices, the four-legged varmints, they'll chew that wire and you'd be like, I don't see any wires that are chewed in half. Well, you can't rely on your eyes. Your eyes are helpful, but not the only tool. You need to know how. So if you measure the circuit and it shows resistance of OL, that stands for out of limits, that's an open. Some people would say it has high resistance and like, okay, that's all right. But if it has OL, like that's so much resistance, it's out of the limits of the meter, that sucker's an open. What am I looking for if it measures open? I'm looking for literally an open. It's gonna be chewed, it's gonna be cut, it's gonna be ripped in half, it's gonna be disconnected. You know, it could be that you worked on the vehicle and you forgot to connect something and it's disconnected, right? Those are all opens. Now, why OL? OL because that meter can measure ohms, kilo ohms. If you guys took basic auto, what's kilo ohms mean?
A lot of ohms.
K means okay, so in a kilometer, how many meters is there? Exactly. So kilo ohms means thousands of ohms. Mega ohms means millions of ohms. And that's as far as it goes. So if it's more than millions of ohms, the meter's like,
Out of limits.
it's out of my limits. I don't freaking know. If it's millions of ohms, that's an open.
Something bad is happening.
That's like not like a little bit of extra resistance. That's like a full on open. But in fact, if I designed the meter, I would I just make the meter say open. But I didn't do that. So when you see OL, it's not that the meter's overloaded and having a meltdown. It's out of the limits of what it can see. It's like, hey, this is beyond millions of ohms. It's out of my limits. It's open. Cool.
1 tera ohm of schoolwork.
I don't know about the giga ohms. They don't do that.
We're into like a thermal event at that point, I'm guessing.
No, an open actually would be such low current, you probably don't have anything. You just, the more open it gets, the more
The
ohms
more
it gets,
resistance.
and we don't really care. At that point, we don't care. You know, it's so much, too much. All right, and then now a short thermal event. A short describes a circuit fault in which current takes a shorter path through an accidental or unintended route. How do you pronounce it? I don't know. Whatever. Take a different path. The low resistance fault causes abnormally high current flow in the circuit and may cause a circuit protection devices such as a fuse or circuit breaker to click or whatever to open the circuit. Hold up.
Now we got too many amps.
I'll leave it on that screen for a second, then we're going to look at picture. I think the picture will help you understand better. So the open meant there was not a good path. That's drastically different than a short, which means the path is too short. Make sense? So I would deal with a service advisor. This is pretty regular. The customer would come in with some electrical problem and he'd be like, oh, so I got to explain a little bit more than I'd like to for you to understand. When I work on the car, I write up my story, and my stories are usually really extensive. I'm detail oriented. Like, for better or for worse, if I see something, it's easy for me to pick out the little details and like defects, and you know that's just kind of the way that I am, right? So when I write my story on what I did and how I diagnosed it and the exact steps, I'm very, very, very detailed. My stories are longer than the service advisors would like. It'd be like a whole page for something minor, and they'd be like, I'm going to summarize this. Check the system, found a short. And I'd be like, no, I didn't find a short. It's an open. And the service advisor's like, whatever. Like, it's electrical problem. Shorts, opens, shorts, and opens are the same thing. No. Open is open. Short means it's taking a path that's too short distance. Those are two different problems with two different symptoms with two different repairs. I have to tell the service advisor, no. You copy what I wrote and you write that in. No. Because if anything ever goes, to, if I fix something and they have a relative read it and the relative reads, the fuse was blown, technician found open. Opens don't blow fuses. If I say there was a short, that blows fuses, right? They are very different, totally different, not interchangeable in any way, okay? So just so you know, the short is a short path that can overcurrent, which could blow the fuse. If there is no fuse or the fuse is oversized, that's when we can have said thermal event, right? The fuses are there as, I'll help you understand this, a sacrificial lamb. Will this help you understand? That lamb is there to protect the circuit. It basically, yes, it's kind of sad. And I'll say some things just so you make sure you remember it. The fuse is not there to help the circuit out, give it extra power. it's, if something goes wrong, if there's a short and too much current goes through,
It'll die for the safety of it.
bingo.
Scapegoat.
Bingo, you know, you could call it the scapegoat, I like this artificial name myself. So the fuse is purposely a little small, so that when current goes through, the whole system's gonna start heating up, but the fuse is smaller than the wire, and so the fuse is gonna burn first. And the fuse is encased in a little plastic, and when it burns, it just goes more, it's like, poof. You can actually hear them, if you ever hear a fuse blow, they kinda snap. Then you look and it's just like blown up in black and
There goes
it's
my-
separated. So if you look at the fuse like this, you'd be like, oh, there's an open. Fuses that blow are now open. Makes sense? A short in the circuit most likely caused the fuse to become open because it sacrificed itself. That's totally normal. I mean, it shouldn't do that, but that's the way the system's designed. It's normal for the system, but if a fuse is blowing, there's something wrong. Okay. Now let me look at a picture here. If we were to look at, let's say that we were to have a short circuit, I'm gonna put this up. I'm gonna definitely remember not to write on the screen, but I'm allowed to write on the whiteboard. Let's just say you've got right here, we'll do just a brief overview of what the components are. Get over here. This is the positive of the source, right? Yeah, the battery. This would be a wire. This thing, do you remember what this is? The switch. The switch controls. The switch does controlling. Cool. Then this is the bulb, which a lot of times we'll call the load. Right. So if we were to do crazy Ohm's law stuff, you'd find out this may have about 4. Let me write it bigger. 4 ohms. The amount of ohms it has is going to slow the current down, right? So if it has 4 ohms, that's, you could do the math and we will, but just know that's going to limit the amount of current. This system is designed to be like, hey, what type of bulbs we're going to use? Oh, we're going to use 4 ohm bulbs. Chillin', that means that with a 12 volt supply and a 4 ohm bulb, using Ohm's law, they can determine the number of amps. Is it 3? I think it's 3. Whatever. You do the math on Ohm's law. This circuit should, let's say we're going to make it potentially enough to flow 10 amps. Okay? If it's going to be 10 amps of flow, we'll size the wire to handle maybe like 10. Now we'll make it so that this circuit is going to flow 10 amps. Let's size the wire so it can flow 15 amps. Cool? And then let's make the fuse 10. Make sense? So if this bulb is fine, it should really flow maybe like 10 amps at the max. That shouldn't blow the fuse. Let's say it flows like 9. Or even better yet, let me put it in reverse. I should have thought about this a little bit more thoroughly. Let's make the fuse. I knew there was going to be some impact guns. Let's make the fuse a 15 amp. Cool? But this circuit should normally just flow 10. Okay, let's say it flows 10. Is the fuse going to blow if we're flowing 10?
No.
What happens if we all of a sudden flow 20 amps? What happens?
It's gonna blow.
Fuse goes, psh, boom. Why would we ever flow 20 amps? If you think about the relationship, why would the amps go up? You remember Heinz law? How did we get too much ketchup flowing out the bottle? Could have increased. You could have increased the pressure, but batteries don't get. The battery can never make like
Not
30
enough
volts.
resistance, right?
Exactly. Boom.
Okay.
How do we have not enough resistance? Remember that word we were talking about with the S, the short? Let's just say you went to have your wiring done for your radio, and you have your radio technician. His name's Sparky. Sparky goes ahead and works on your radio. First off, if the radio technician's name is Sparky, I don't think I'd go there. It's kind of like taking your place that does window tint, Bubbles the window tint guy. I don't think I'd go there. Make sense? Okay. So Sparky goes and does some work, and right here, you see that? That's a screw. If Sparky shoots a screw through your wire and into the ground, where's the electrical current going to go? Electrical current's supposed to leave a positive, go through the switch, go through the bulb, which slows it down, right? Instead, what's it do? It goes up and it says, oh, path of least resistance. It goes into this screw and into the ground. Do you see how the circuit just got shorter? What happened to the resistance?
Gone.
Right, so like in Heinz Law, right? If I were to accidentally pop the cap off and turn it over, blip, all the ketchup is out. Make sense? This would have too much current flow because it's a short circuit. Electrons are like this, like la da 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 da. Go through the load where it's kind of difficult. Nah, I'll just go right here. Excessive current blows the fuse. That's a short, okay? Now we're gonna set up shorts. We're gonna measure shorts. We're gonna wear shorts when it gets warmer. We'll do all sorts of stuff with shorts. But just so you understand the term, a short circuit is a shorter path with less resistance, and that's gonna cause too much current, hopefully blow the fuse. If Sparky wired it and didn't use a fuse, though, there is no fuse. What happens if there is no fuse?
It's gonna overheat and it's gonna damage the amp or something.
And it might catch the wire on fire because the insulation can get so hot it'll burn. That'd be scary. That's one of those thermal events. Cool. Now, this is something different. This is an open. Okay? An open circuit. Why is this one open? Can you tell? Is there continuity here? Electrons leave the positive and they go to the switch. Do you think that they can jump this gap?
No.
They don't jump the gap like that. This circuit's open. Why is it open? Switch is open. Yeah, did you know? I mean, if your headlights don't work, it could just be that your switch is open inside. You'll turn it on and the switch might not make a good contact right here. That's an open circuit. Can you see that though?
No.
You can't. And that's why you have to know how to measure. Make sense? So I'm going to teach you how to measure for opens, measure for shorts, etc. I'm not going to give you fashion advice about your shorts, but I still have shorts that are jeans. Jean shorts. Jordans. But I'm not going to be wearing those. You like that, huh? Okay, so then talking about like a short circuit would be, see these windings? The electrons are supposed to go round and round and round and round and round and round and round, but this winding shorted to this winding. Did the path get shorter? Yeah, too much current. That's going to be a problem. That's a short. This one's actually a really cool example. This one, electrons leave the 12-volt battery, go through the fuse, go to the brake light circuit, and then look what happened right here. This has a short to ground. That would be like the Sparky thing. Maybe the wire got pinched when you were working on it. Maybe from the factory the wire was just rubbing and it does a thing called chafing and it'll chafe the insulation off and now you have copper wire touching bare metal. Those would all be shorts. This short is going to blow that fuse. And then you're going to put another fuse in, it's going to blow that one. Then you're going to be like, oh, it's blowing the 10 amp fuse. Let me put a 20 in there. Makes sense. And now the 20 amp won't blow. Instead, it'll catch the car on fire and burn it to the ground with the occupants inside. And you're going to go to jail. We're going to see you on the news.
Everything's gone wrong.
Everything. It's all over. Makes sense?
Terrible.
We don't do that. Now, if you knew nothing, you could think putting in a higher amp fuse is better. Okay, but now that you've been in class, the fuse is sacrificial. If the fuse is blowing, the circuit has a problem. The fuse is the only thing preventing that family from being burned alive inside of the car. You know why I make it so? I want to make you pay attention. Okay, it could probably never happen, but it could. It could happen. All right, and now this one's much more abnormal. Short to ground is the typical. Short to power or voltage is different. 12 volts leave the battery. By the way, we're going to do circuit tracing, so if you're not getting this, like, don't, just chill. I'm trying to get you to understand the terms, not so much be able to predict voltage. That's like a whole 2 or 3 weeks. Leaves the 12-volt battery, goes to the brake light switch, but the thing is, this wire shorted to this wire, so even if you have your ignition switch, let's say you turn your ignition switch on and your brake light switch is off, the 12 volts wouldn't stop here. It would go around and power your brake lights all the time anyway. So short to voltage is sort of like, this shouldn't be getting power when you're not stepping on the brake lights, but the brake lights are stuck on all the time. Make sense? Why are the brake lights on? I'm not stepping on the brakes. They could be shorted. This wire might have got pinched to that wire. Make sense? That's a short to power. So a short generally means a shorter path, but like in this case, it's not actually a shorter path. It's having to go the long way around, but that short to voltage is keeping the component powered when it shouldn't be. What's this customer's symptom?
Brake light stay on.
The brake light stays on, and what do you think? What if does the
Battery
customer,
drains.
Bingo. The customer may come in with a simple concern. My battery's dead in the morning. I jump it, and then my battery's dead the next day, right? So they don't come in and say I have a short. They come in and say my battery's dead. Then you may find the brake lights are on. Then you may track down there's a short right here, right? So you got to be able to peel that onion in a way, right? You got to be able to get down to what's really wrong. Make sense?
And you gotta remove the layers.
And then you can bill them. That's why we take the money. We provide goods and services in exchange for money. That's what we do. But you got to be good at it. You don't just get to take people's money. And you go to jail for that. But if you're good at it, the customer will willingly be like, "My battery's dead every morning. Can you fix this for
Should
me?"
be
And you'll
justifiable to take
exactly.
money.
Yeah. And they'll be like, "Yeah," but it's not gonna be cheap. And they say, "Well, nobody else can figure it out."
What if I'm just really good at taking people's money in the first place?
You could probably be some sort of a salesman. But I don't do sales. Okay, there's some other short circuits we could have. There's other types of faults and defects we could have. So let's say we had a high resistance fault. That's not an open, that's not a short, it's kind of different. We might have a bulb that's dim. It's not stuck on. It's not totally inoperative. But when you step on the brake lights, the bulb is dim. Dim would probably be high resistance. The high resistance could be here, could be here, could be here, here, here. But in this case, this actually had a high resistance on the ground. That would cause a dim bulb as well. The problems don't only occur on the positive side. They occur on the negative side too, depending on what the issue is. Cool, so a high resistance fault, that might be, let's say that a wire got a little nick in it and water got in through the insulation and it started to corrode the copper and the copper turned green. It's no longer a very good insulator. It's no longer a very good conductor. It has resistance in it because it's corroded and oxidized, and the water really ruined it. That's what it is. So when we do wire repairs, by the way, we need to make sure it's watertight. If it's not, water will corrode. Corrosion will cause high resistance, dim bulbs, slow motors, etc. And the other aspect to look at this, the high resistance causes an excessive voltage drop. Okay. So if we were to go back to last week, part 1, remember there's the parents and they got a $12 allowance they hand down to the kids, right? If there's an unintended load in the circuit, now that voltage has got to be shared, remember? So this one's like, hey, I was thinking 12, but this one's like, yeah, buddy, I'm taking 6. Have a nice day. And then it's like, oh, I only get 6, I'm going to be kind of dim. You know, these types of things. That's a visual to me. Make sense? So the unintended resistance will cause a voltage drop, which will make the dim. It's lower amperage, but it's also a voltage drop. A lot of times we diagnose circuits using voltage because low amperage you can measure, but you don't know where the kink in the hose is, whereas pressure measurements can diagnose where the kink is. You'll be like, oh, okay, 12 volts here, 12 volts here, 12 volts here. That tells me all this is good. 6 volts here, there should never be 6 volts after the load. That means there's another unwanted resistance after load. Cool, so like, just so you know the terms, we will spend nearly a month on trying to get you to understand what the heck I just said. It's pretty, if you can understand what I just said about the voltage drop, you're gonna be like, well, you'll be an electrical tech. For real. Okay, like I was saying, sometimes I get ahead of myself. Voltage drop testing is the best way of finding high resistance in the field side or the ground side. Cool. So measuring voltage can indicate excessive resistance. Kind of makes sense. And then let's say overall, yes, it's reducing the current flow. The high resistance fault could be excessive. It might even reduce it enough where it could be an op. I mean, if there's a whole lot of resistance, that can make the bulb totally inoperative. But again, we're going to measure the voltage drop. You can measure voltage drop in a couple different ways. So just a couple terms to keep in mind for next week. Available voltage and voltage drop. We're going to be doing both of those. Make sense? Okay, pretty good. And then here we jump into voltage drop testing the positive battery terminal coming off an alternator. So this is an example where the customer comes in and says, hey, my battery's not charging correctly. Could that be an alternator problem?
Yes.
So Mo, my buddy, the mechanic,
I just wrote this.
you know that guy?
Yeah.
Mo, yeah, Mr.
And
Canic,
what was it?
mechanic.
Voltage drop and
He
what
puts
was
an
the other?
alternator on that sucker. Be like, oh, it ain't charging. I know, Daddy. That's an alternator thing. That pow.
What was the two terms? It was voltage drop. and-
Available voltage
Okay,
and
available.
voltage drop.
Okay.
Okay, so Mo puts an alternator on there, and it doesn't fix it. So you know what Mo does? Goes back down to where'd Mo go? O'Reilly's, Napa, AutoZone,
Advanced
AutoZone.
Auto Parts.
O'Reilly's. You know, like Advanced, whatever. You got it. Napa. He goes down and says, "Hey, this alternator is no good. Yonke. Give me another one." And the guys behind the counter are like, oh, this guy, he always replaces like 2-3 times. So he gets another alternator, puts another alternator on there, it doesn't fix it. So what's Mo do?
Put another one.
Maybe the third one will fix it. Yeah, like your sign was when the first one didn't fix it. It's probably not the issue. Excessive voltage drop will cause this. So what you could do is you could actually put your meter here and your meter here, and you can measure how many volts are dropping across the wire. This is stuff we're going to get into, but just to preview, that wire should not be dropping 1.27 volts. That means if your alternator is working pretty hard, it's charging at, let's say, 13.5. By the time it gets to the battery, it's only 12, or like 12.3. That's not high enough voltage to keep your battery really charged. Exactly. It's dropping voltage on the wire. It's not that the alternator's bad. We just tested, we proved with our meter, we should never have a 1.27 volt drop on a wire. There's something wrong with that wire. We need to replace the cable. Cable will fix it, 3 alternators won't fix it. 4 alternators might though. That's what Mo said.
Maybe 5.
Maybe the fifth one makes all your problems go away.
Lucky number 8.
Uh-huh.
Lucky number 70.
7?
No, 17.
7 times 70? Okay, and then we talk about electrical sources, okay? This one it's really scientific, but it's kind of cool. So, talk about energy, can be in many forms, maybe transferred between objects, can be converted in different forms and states that can be harnessed to accomplish many types of work. All right, okay. We're talking about like thermodynamics or something. You guys know that energy cannot be either
Destroyed.
created or destroyed, right? We just move it around from thing to thing. The way the universe works is pretty amazing.
That's because no one's found a way to destroy it yet.
You may be that guy. You hear that evil laugh? He might do it. Okay.
I'm going to destroy the universe one day with logic.
I don't think you got enough of that.
I'm a man. I need to report this. Let me get to my computer. Okay. So electricity is unique since it can not only be transformed into thermal energy, light energy, chemical energy, mechanical energy. It can also be created easily. So we really love electricity because we could do a lot of stuff with it. I know Humberto may be back any second, so I'm just gonna help him. All right, so our cars, a lot of times we'll use this electrical energy for these reasons. We could do a lot of stuff with it. For example, thermal energy. Why do we want that in our cars? You want to toast those buns on the way in this cold, foggy morning, didn't you? So we can use electricity for that. We can warm up our rear defogger. We can do all sorts of stuff. How about light? That's important for
We
the
need to
nighttime
see.
driving. Exactly. Chemical energy is kind of an interesting one. The battery is chemical energy. Okay, so just so you know, when we charge the battery, we change the chemical composition, and when we discharge it, we change it back. The battery chemically stores our energy for us. Okay, it's kind of a cool thing. And then mechanical energy, like motoring, Mason when he gets that e-bike in. Right? Electricity can do some cool stuff.
I still remember that.
Oh yeah, it's gonna happen. And we can also, it's easy to transfer. We can generate it, right? So when we say generate electricity, we're not making new energy, right? Because we can't create it or destroy it. But we could burn fuel, gasoline, fossil fuels, dinosaur stuff, things, and whatnot. Dinosaur fuels, things, evil things such as dinosaur stuff, and we can transfer that into electrical energy, which is so much better in things, right? But that's what we do. If you want electricity, we can do that. Burn this oil, harness it through an engine, and make electricity. Cool? We do that. We do that. We do that a lot, actually. Okay? And then, like, if you want to test electricity for fun, you can use static electricity. Like, we don't have a whole lot of thunderstorms here all the time, but when you do, you notice the lightning comes from the cloud down to the earth. That's a difference in electrical potential. You scrubbing your feet across the carpet and going to your little brother and going, pow! It's actually more fun. Versus you're observing it. You're observing this, okay? And generally, this is just saying, warm and cold air fronts meet. Warm air contains water droplets, and usually a positive charge rises up. The cold front, which contains ice crystals, the negative charge sinks. As the water droplets and ice crystals collide, it makes static electricity. And that buildup will periodically equalize with the earth and with a lightning bolt. Pretty awesome. Cool. So that's electricity. There you go. This is not where you want to be. You want to be somewhere else. Make sense?
Not good.
Not good. Okay. And then we talked a lot about the source. So basically that electricity is going to be stored in that cloud until the conditions are just right, where it will be released in a bolt of lightning. Cool. And then again, this is very important. Electricity can be produced by moving a conductor through a magnetic field. That's kind of how like a generator works. Applying pressure to a special type of crystal. Did you know that? Interesting. We use that a lot of times in knock sensors. So piezoelectric crystals. If a piezoelectric crystal varies with pressure, it'll actually produce voltage. So for example, if an engine was knocking, like knock, like that varies pressure, because that's how your eardrums work, right? That knocking varies pressure, the crystal picks that up and it makes a little pulse of electricity. The computer can see that and know that the engine's knocking because it's seeing pulses. Cool, so we're generating electricity through a crystal based on engine knock. Cool. Converting sunlight into electricity through photovoltaic solar cells. So like PV system, PV solar. If you have solar on the roof, that's a PV system. When you submit those plans to the county, they don't want to see solar on the title. They want to see a photovoltaic system. Why? I don't know. Because
they're nerds.
it's just the way it is. It's how the engineers describe it. It's a photovoltaic system.
We all know engineers are always wrong.
Something tells me you may be an engineer someday. You got the look, you got the laugh, you got somehow you're trying to get even with people behind the scenes and be like, oh, let me put the drain plug here.
Maybe.
Sliding by people you don't even know.
Maybe.
We could proceed with some jokes about the technician and the engineer, but we won't. Chemical reactions that take place inside a battery. So that's what's happening in the battery. This is a chemical reaction right here. This battery. Cool. When we get into batteries, we talk about lead acid, talk about absorbed glass mat, lithium iron phosphate, you name it. Chemical reactions that store electrical potential. Pretty neat. Lots of sources. Static electricity can be produced, for example, by rubbing two insulators together. Generally on the periodic table of elements, the majority of materials are insulators. And sometimes, like, if you're rolling your cart through Costco, that rubber wheel rolling across the concrete floor will generate some static. And then you go to open up the freezer thing and be like, oh! Right, so we're generating it pretty easily. especially as the insulators rub against each other. One material will lose electrons to the other, and as they move to the other, that one gains a negative charge. And when the charge gets high enough, that's when it'll discharge. So like when you reach for the freezer door, you're charged negatively through those wheels rolling across the concrete, and then that freezer is neutral or not negatively charged, and pow, you become equalized right there. Cool. Okay, and over, it's repeatedly until there's no more room in around your body for extra electrons, which you probably never get to that point. Now, we're going to finish electrostatic and then we'll take a little time. Okay. Negative charge of static electricity builds up, creates an imbalance, and that's the pow. Cool? Especially if you touch something positive. Or, more accurately, when you get in, what's this word mean? Close proximity. The higher your negative charge is, the less close you have to get. So if you're just a little negative, you'd have to actually touch it to equalize it. But if your negative charge builds up and builds up and builds up, you only just got to get close to something that's positive or neutral, and you zing, bow, there it is. You made mini, tiny, but still very impressive lightning. Impressive in your own way. Okay. And you could say static electricity is capable of creating large and powerful sparks, but you're not. Realistically, it's not going to be that. You're probably not going to make that much. But those lightning, think about that. They can make an immense amount of energy right there, and they can ignite flames, flammable vapors. You know, we figured this out. Where do we use this every day in our engine? Use sparks, which are sufficient to ignite. Oh, that's right. The bujías, right? So the spark plugs get a very negative charge out of the coil, and we send it down to the spark plug, and then we make it arc a gap to the grounding electrode, and when it arcs that gap, we've already got air and fuel all compressed, ready to go, and then that arc occurs, and it's like burning, baby. And did you know, when we're burning that fuel, what we're actually doing? We're breaking the chemical bonds in that hydrocarbon, gasoline, and the air, and we break those chemical bonds. We're removing energy from those bonds in the form of heat, which build pressure, which push the piston down, which make the crankshaft go around, which makes the wheels go vroom, and also charges the battery through the alternator and etc. So really, this initiates your car. I'm sorry to let you know, is already electric. It's just electric that's bringing out more energy from gasoline. Okay, just the way it is.
A generator.
It's pretty much. I mean, we're using electricity to extract energy from gas, and then with a generator we use gas to create electricity, but we kind of do both in the car. We're using electricity to ignite the fuel, then we're using the fuel to turn the crankshaft, and that motion turns the alternator, which recharges the battery. It's this whole back and forth. Energy is being passed all around your car. Not created or destroyed, but just change it to this, change it to that, change it to this, change it to that. Make sense? But you got to put the go-go dinosaur juice in there to charge that battery. Yeah. Cool. And
They
then,
went extinct once, we'll make them go extinct again. Just make
and
it-
then this right here is where we were talking about. You don't shuffle your feet over there and then go pow, because you'll build up a negative charge of static electricity. Cool. This is a lot about electrostatic electricity. So remember what I said about pumping gas? Ground yourself. Touch something that's a good ground before you touch the nozzle. It's actually a good safe bet. Okay? So with this, let's take just a couple minute break. Priscilla? Just push pause. Alright, so moving on from static to thermoelectric. You can kind of tell what it's about based on the name. Thermal meaning heat, right? Heat can be used to create electrical voltage signal. Did you know that? If we heat and cool things, we can change the voltage level on there. So if we have two dissimilar metals, they're joined and heated to this particular point called the hot junction. you. The whole device is called a thermocouple. So I want you to remember this term for a bit.
So if there's a hot junction, does that mean there's a cold junction?
I'm not exactly sure. Okay, in a way, there's no such thing as hot and cold. Hot means more energy and cold means less energy. I think we're only concerned about the point where it creates this voltage. So if we use these to create a thermocouple, we could do a couple things with this. We're mostly focusing on how if we have dissimilar metals, they can be used to make heat. But the thing is we can join these and then the amount of heat it has can actually change the amount of voltage it makes. So why do you think that might be helpful? If we have a thermocouple and what I just said is the amount of heat it has will change the voltage, how can we use that? So if the heat varies, what does the voltage do?
Varies as well.
So I'm saying this is kind of like a sensor. Yeah. A thermocouple is another way that we can measure heat, right? So while this is true, heat can be used to create an electrical voltage with two dissimilar metals. What I'm kind of saying is you can use that design to basically measure things. So you guys know about thermometer, right?
Yes.
A basic thermometer, let's just say it would be like a mercury-based thermometer, would have a bulb of mercury right here, and the hotter it got, it'll actually rise up a tube, okay? So you came in late, now you're gonna be quiet. Right here, you two need to be split up or what? So the hotter that mercury gets, that mercury's gonna rise up a tube, and it's gonna indicate a temperature, cool? That's fine, but what if you wanna measure something much hotter, where the mercury would actually like blow the tube up? We could use a thermocouple. So if you want to be able to measure higher heat with a lot of accuracy, and let's just say you're trying to measure a burner on a stove, you're not going to like hang your thermometer down there. Like that's kind of ridiculous. You could use a thermocouple, put the thermocouple near it. The thermocouple heating up will give you a different voltage, and that voltage will read in a temperature in degrees. So. But the theory is based on dissimilar metals that create electricity when it's heated, okay? When the heat's applied, a small electrical current's generated for a temperature rise of around like 200 Celsius, okay, but I don't like Celsius, although that number makes a lot of sense. 392 degrees Fahrenheit will get about 9 to 15 millivolts if it's loaded, and about 30 millivolts if it's unloaded, okay? So I'm saying like this is a way to measure temperature. Okay, and we'll use voltage. Don't worry, you got the recording. Okay, so this is kind of what we're showing here. This thermocouple, using this nickel chromium, nickel aluminum, we'll combine those two. As we heat it, that will create a voltage, and this essentially will become like a reading we can translate to degrees. Make sense? Because you kind of don't really care how much the voltage is, right? You can be like, oh, that's 30 millivolts. Yeah, but what's that in degrees? Cool? So if you remember, it was, what was the number for 30 millivolts? Like 392 degrees Fahrenheit, makes sense? So we can indicate temperature really accurately with this type of system. And this is actually a thermocouple for an EGT. Anybody ever heard of an EGT? Exhaust gas temperature, yeah. So we have diesels and we need to measure the exhaust gas temperature, no problem. We build a thermocouple, we put a thermocouple in. This thermocouple will make a voltage and report back to the computer. The computer will see the millivolts and say like, oh, that exhaust is 392 degrees or whatever the number is. Cool. So again, just another type of electrical component used as a sensor. And then to generate a larger voltage in the presence of heat, we'll use multiple thermocouples in series. Thermocouple, 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 thermocouple. That'll help us to be a little more almost like zoomed in, right? Because if one thermocouple creates 30 millivolts at 392 or 82, whatever it was, if we're to have several, it'll increase the voltage more and more. The bigger the voltage change, it's almost like you can see a small temperature change better. Kind of makes sense? We'll put a whole bunch of thermocouples together, and if we pile a bunch of thermocouples on top of each other, you know what we call it? Thermopile. which is capable of generating like 450 to 750 millivolts. And then how can we test it? Well, how do you think? If this is a thermocouple and we're looking at the millivolts, how could you tell if the thermocouple's working?
Checking the volt.
And what would you do to make the voltage change?
Turn it on.
Heat it up, yeah. If it's in the exhaust, yeah, start it and see if it goes up, right? That's how we test them, checking the volts, exactly. So if you could also, by the way, go in with the scan tool, go to the computer and look at the live data. That's probably how I would check it. But if the live data was not reading correctly, now you're not sure, is the problem the thermocouple sensor, is the problem the wires, right? So we will resort to getting the meter out, measuring the thermocouple directly. If the thermocouple works, but the computer doesn't see it, it could be in the wiring or in the circuit. Makes sense? So we'll start maybe with the scan tool, change over to the meter. And again, this is just the zoomed out big view of all the different electrical sources and components and how it's generated and the overall. I don't expect anybody to be able to measure thermocouple voltage today. We got like a whole semesters where even to the point where you're going to diagnose a headlight. Okay, and then here's kind of a fun one I'll tell you about. Remember how I told you I end up diagnosing all my own stupid stuff?
Yeah.
The problem is, when you're on top, where's the only direction you can go from there?
Down.
It's kind of a scary place to be. So I feel like I'm batting 1,000. I fixed the fridge, I fixed the dryer, I fixed all this stuff, and then on a cold night, the heat stops working. And my wife says, "Hey, it's getting cold in here," and I feel the air coming out of the vents, but it's cool. And I'm like, oh. And see, this is the thing. Remember, I'm batting 1,000. I'm on top. I think I'm on top. She's going to expect me to be able to fix it. I'm like, I don't freaking know about the furnaces. And so sure enough, I feel it. Cold air is coming out. I go up and I listen to it. And you can kind of hear like it kicks on like the fan. And then you hear the blower for the fire part of the furnace kick on like for like 20 seconds, and then it shuts off. Right? So it's hot for like 20, 30 seconds, and then it's done. And I'm kind of listening and looking, not really being an HVAC technician, but just thinking like, it seems like the gas can flow and make the flame, and it starts to blow heat, but then after 20 or 30 seconds, it shuts down. So I'm just kind of going over it in my mind. And then, of course, I'll be honest with you, I cheat, and I just start like YouTubing and Googling and trying to learn, but that's fair. You gather information however you can. And I did find somebody who explained it. They'll open the valve and the gas will flow through and it'll go, but then after 20 or 30 seconds, it's going to look at its thermocouple in a gas-fired appliance to prevent raw gas from being vented into the home. Let me break that down for you. This is the way I like to make it kind of simple. Keep it simple, stupid method. Not that I'm kissing you, I'm just saying KISS, K-I-S-S. Keep it simple, stupid. Like, it's okay. The gas comes on. How does the furnace know if it's being burned, or if, let's say, the igniter's no good and it's just injecting natural gas all throughout your house? Does that sound safe?
No.
No.
So I use a thermocouple. It waits 20 to 30 seconds, and if the gas is making a flame because it's ignited, what should happen to the thermocouple? It should get hot, and what should the voltage do?
Increase.
It should go up, exactly. So they use the thermocouple to tell, did the furnace fire up or not? And all in the course of like an hour of mostly me learning from a couple other people and being like, I don't think that thermocouple is reading an increase. I'm able to check it with my meter, it shows no difference. I find another video where they're like, they call it a flame sensor, but it's really a thermocouple, right? So I'm calling a thermocouple to you, but whatever, call it a flame sensor because it's sensing if a flame's occurring. Pull it out, clean it up, put it back in. The house is warm. She's happy. I'm thinking like, man, one of these days,
Batting 1,000.
I'm not gonna be able to fix something, and I don't know what I'm gonna do. Okay, but that's just kind of fun because this stuff, you're not gonna work, as far as I know, not gonna work on furnaces. If you can really learn all the aspects of automotive, next thing you know, refrigerators make sense. My dryer had a bad pressure sensor. The thermocouple in the furnace. The generator went down at one point. That was a pressure regulator. Like, there's just
You're just learning technology as a whole.
stuff. And so that's what I'd recommend to you is, like, don't think this is just so you can constantly fix cars. If you can grasp the overall concept, you can go fix some other stuff too, because we're copying each other really. Cool. And then sometimes you use and develop engine design, so they want to measure heat in the engine. The engineers that use this. It's kind of hard to measure stuff like spark plugs with that thermometer, so that's why they're using the thermocouple, exhaust thermocouples, etc. They'll look at the exhaust gas temperature to fine tune to get the lowest emissions, right? This is more in the engineering field, more so than repair sometimes. Now we talk about electrochemical. This one's different. For example, two dissimilar, you know what this word means?
No.
Different, just different. We could say different, not the same. In automotive, sometimes we use terms that are like, do we really need to call it dissimilar? It just means two different types of metals are immersed in an acidic liquid, so like battery acid, called an electrolyte, not like Gatorade. Do not consume like Gatorade, you die. All the way.
But can you
Permanently.
use Gatorade to power to as
I
battery?
I know Gatorade contains electrolytes, but I wouldn't consider Gatorade itself a whole electrolyte. This is battery acid. The breakdown of the chemicals into charged particles called ions result in a flow of electricity. What? So the difference in the dissimilar metals, right? The lead sulfate, whatever, in an electrolyte will actually generate current flow. You know what that means? Make electrons move. It'll end up with a positive voltage that can cause a certain number of amps depending on the size of the plates and the charge level, right? This process called electrolysis is applied in a standard lead acid battery of automobiles, okay? This is a flooded lead acid battery. We've got different plates separated by an insulator, and then this whole thing is going to be filled with an electrolyte like a battery acid. As it discharges, it becomes more like water. As it's charged, it's more acidic, and it's going to make a higher voltage difference between the cells, right? So when you put the battery on the charger, you're literally transforming the more watery battery liquid to like a more acidic battery liquid, and that'll make a higher voltage. It's crazy to think all that electrical energy is stored in the chemical part of the battery. That's why it's an electrochemical. The electricity is stored in chemical form in the battery. Cool. There are two types. Standard flooded. That's this one. It gets filled up and it's wet. It's liquidy in here. Or what's this other one? What do they call the other one?
The gel one.
Oh, it's kind of like a liquid electrolyte and an absorbed glass matte battery, which uses electrolyte paste. You can call it gel battery. They'll be like, give me a gel battery. That's a pasted gel, whatever. It's an absorbed glass matte. This one doesn't have liquid in it, I could tell. If I were to read it, it's going to say something about AGM. This is, sometimes they'll call it a non-spillable. It doesn't really say a whole lot about it. Here we go. This one specifies AGM. It's a similar type of electrolyte, but it's absorbed into the mats, but it uses the same technology. It's just the difference is this is in a motorcycle or an ATV. Did anything spill out? That's good. Like sometimes motorcycles end up tipped over, upside down and stuff. We wouldn't really want to use a lead acid if we can help it. That's kind of why. We will go into a lot of detail in batteries because we're going to cover batteries as its own unit. But for now, batteries don't generate voltage on their own. They store voltage from another source. So let's say the battery can't generate anything, but it can store it. You can put energy into it and you can save it and then you can take it out later. But the battery doesn't generate it. Make sense? Just so you know, it's a storage device. That's it. Pretty cool one. Negative plates. This one is coated with a gray spongy lead grid. Positive plates. Oh, actually, this has lead peroxide. And then there's some separators, and that's generally going to focus on. And then if you were to, look at what do we do with the battery just sits there until you go to start the car. At that point, you demand that battery give up some energy to turn your starter motor, right? So when you go to crank it, it's actually going to take, we'll say traditional again. Positive, gonna leave the positive terminal, turn the motor, go to the negative, and that's actually gonna move your starter motor. So it's kind of weird, but your alternator takes the movement through magnetism, makes it into electricity, puts it in the battery changes chemical composition to store it, then when you want to start again, it basically gives it back tomorrow. Your alternator charging the car today will be your battery starting the car tomorrow. It's kind of crazy, huh? It might not be, it might be earlier today and later today, but right, your alternator puts electricity in the battery stores it until you want to start it. When you want to start the engine needs to be turned. It needs to be turned. You know, back in the day, they used to go out there with the crank and crank it over. Like, yeah, those were hard days. Now you turn the key, and the starter's going to crank it as long as your battery has enough energy in it to crank it. That's the whole purpose of the battery, really. Also acts as a buffer, because your alternator tends to be a little rough. The battery smooths everything out.
DC.
Voltage level, yeah, DC. Okay. Your battery is just like we described a cell. It's multiple cells. Boom, boom, boom. 12-volt battery contains 6 cells that generate 2.1 volts each. If it's 2.1 volts each, and there's 6, what should your voltage be? And that's why we call it a 12 volt, but it should be a 12.6 volt if it's actually charged. Cool. Now, photovoltaic, that's the solar panel system. It's made from a semiconductor. It converts sunlight directly into electricity. Your solar panels can't exactly power your home. Your solar panels generate the DC. Your inverter makes it into AC, but understand, it just makes as much as it could possibly make. If it's sunny, it's making maximum. If it's cloudy, it's making minimum. And anywhere in between. That's all it does. These don't this is hard to control, kind of. And you can't store it. So if it's direct, what happens when it's dark outside? Can you power your house?
No.
No. So what would you need to be able to power your house at night? How would you store it? How are you going to go off grid when it all, when it hits the fan here? You have your solar panels directly charge your battery, which will store it so you can make it through the night, and then tomorrow your solar panels charge your battery again, or whatever. Now, of course, you need something to control it, right? Because if your solar panels are putting out too much and your battery's already charged, you need an inverter, like a charge controller, to kind of chill that out. But that's kind of like the concept of going off grid, being, energy independent. What we really do on 99% of the homes is we're tied to the grid. When your solar panels are producing max, you're pushing it back to the grid, and the grid is allegedly storing it for you, or maybe you're helping to power your neighbors' homes on the sunny days. But they have a hard time harnessing that, and sometimes they ground that, if we're overproducing solar, they'll just ground it, be like, get rid of that. Be like, well, that's good electricity. Yeah, but it costs a lot to store it. Batteries are expensive. So, but then on a cloudy day, we're getting electrical from the grid from generators. What's powering them? I don't know. Probably not gonna be nuclear now.
This is why nuclear
Probably be some
energy
be
is
with
the
that
true
dinosaur
future.
stuff. Mm-hmm.
So
So
tasty dinosaur oil.
delicious. Okay, so consider that. But in a car, though, this is more applicable to the car. Sunlight's absorbed by these materials, and the photons knock electrons loose from their atoms, causing the electrons to flow through a material to produce electricity. Boop. That's the solar sensor. Remember the one on the dash? The sunlight comes in, it does this reaction, and it generates a voltage based on your sunlight amount. If you don't have a whole lot of photons knocking loose the electrons, the computer's going to say, turn on the transistor for the headlights. Like that. Make sense? Like that. That's the real science aspect of it. Cool? The process of converting light electricity is called the photovoltaic effect. That's why it's a PV system. When the light energy strikes the surface of a PV semiconductor material, these materials emit electrons that flow in a circuit to perform work. That's what a solar panel does. That's what the solar sensor in your dashboard does for your automatic lights. Make sense? That solar sensor, by the way, is also an input to your air conditioning your heating, ventilation, air conditioning system, because if you want to feel cool or you want to feel warm, it depends on if it's sunny or not sunny, right? You ever notice you go outside in the shade, you feel cold, but in the sun, you feel like, oh, it's so much warmer? The air temperature didn't change right there. Maybe not even a half a degree. Why do you feel so different? The sun warms your body directly. Well, your HVAC system needs to know, is it sunny or is it shady? And if it's sunny, decrease the heat or increase the AC. But if it's shady, you better increase the heat or decrease the AC, all to make you feel good. We want you to feel good. We need a solar sensor to make you feel good on this automatic air conditioning systems. If you got manual and you're using the sliders and the things, like you don't have that. Never mind. You have to adjust it yourself. But if you have a car where you can get in, you can set 68 degrees and just, it automatically does it. Trust me, it's looking at your solar sensor to see if it's sunny or shady and fine tuning it behind the scenes so you feel good. You do you, dude, in true California style. Cool. So, and by the way, we need to be able to diagnose these. So when this sensor fails, you have to kind of have an idea like, hey, how am I going to diagnose this, right? That's why we're looking at all these types of electronics. Okay, and then and as another use, ignition systems used to time ignition sparks. Okay, back in the day, there was a thing, it was called an OptiSpark. The distributor would spin, before the OptiSpark, the distributor would spin and we have little points and sensors and stuff. And they actually found it's really accurate to use a light and shine it through tiny little holes, and when it spins, you can fine tune the exact location of the distributor. And they'll have an LED shining, and they'll have a photovoltaic sensor receiving, and it'll be like, oh, the position is right there. They were using this for position sensors. We don't really do a whole lot of that anymore, just for the record. But we did. We can even use this to some extent with fiber optic. You want fiber optic internet from Frontier, 500 megabytes for $69 a month or whatever. They're using this type of stuff. They'll flash a light at one end of a glass tube, and the other end, a photovoltaic sensor will pick it up, and you can transmit on-off information, because this will give pulses of on-off. Thank you. Yeah. Mm-hmm. Okay, kind of makes sense? And the amount of daylight to operate it, right? It's going to sense the amount of daylight for the headlights. It's going to sense it for your HVAC. Ultimately, we might be troubleshooting one sensor for both systems. Now here's that other one. Remember the crystals? Yeah. The crystals, certain material, generally quartz, and it's going to become a piezoelectric crystal, and that's going to be the knock sensor, right? So they're subjected to mechanical stress. That means they can sense pressure, right? So if you were to set a crystal right here next to your speaker and be like boom, 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 it will actually, those pulses in the air will exert a force on the crystal. It'll generate that voltage. That's the piezoelectric effect, piezoelectricity, and basically listen to your engine. Okay, the best way to look at this is a microphone. And if there's voltage being generated, that means there's sound. Engines make sound, don't they? But they've programmed the computer to say this type of voltage indicates this type of sound, and that's spark knock, and you need to back the timing off. You need to retard the timing a little bit. And sometimes words are offensive, but they don't change for you, okay? So if you want to have the timing be a little later, it's called retarding the timing. The computer does that, and that's because you're supposed to put your 91 octane in, and you put 87, Arco 87, you're like, cheap. Okay, and then the engine's like, hey, I hear a new little something. I hear a little something happening, and then it's like, no, back the timing off. We're going to save this engine, all because of this technology. They'll also use piezoelectric to do a couple other things, like some injectors. If you want an injector to open and close really quickly, you can actually use a piezoelectric crystal, and you applying voltage will actually move the crystal and spray the fuel. And then removing voltage will actually expand the crystal, and it'll close the fuel. But we do some wild stuff. So if you read about piezoelectric injectors, you'd be like, what? Well, I just explained it. It goes both ways. Pressure makes voltage, but also if we apply pressure, it can change the shape of the crystal, and we can, open and close injectors and spray fuel and not spray fuel. And same, we can also use them to ignite stuff, like like in appliances, you know, if you have an electronic ignition, sometimes they'll use a piezo electric igniter. Okay, so it's pretty neat. This is the main function for us. Measure vibration, that's the knock sensor. It's listening. Microphone. Cool. So that's like kind of what it's saying pre-ignition. The ECM is going to see that and adjust the timing. Also, who's ever used a digital torque wrench? Bum, bum, bum. Same thing. Strain gauges designed to detect stress in a component or to detect weight of passengers and determine airbag deployment. If sometimes we use pressure sensors for this too, but if you have a dog and the dog is sitting on the passenger seat and the dog weighs 30 pounds, trust me when I tell you, you do not want that airbag to deploy. But if it's an adult and the adult's kind of on the threshold, they actually want to know the weight. If it's a small human, they'll do like a first stage deployment, which is a little lighter, and if they're a little heavier, they'll do a second stage deployment, which is a little harder. So they actually, this could be like a life hack. If you go in the scan tool, you can actually calculate the passenger's weight. So be like, hey, take a seat. Like you're going on the, you get like, hey, take a seat. Like click, 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 click. You know what's pretty cool about that though? When we go to make sure the system's safe, sometimes we have a calibration bag. So you want to know what a calibration bag is? This is a 50-pound sandbag. You put a 50-pound sandbag in there and you go in the computer, you make sure it says 50 pounds. This sensor measures weight, basically the amount of force. The amount of weight that's in the passenger seat will be an input to the supplemental restraint system deployment. It's really wild, some of the stuff that we do with these sensors.
Which specific sensor measures the weight?
It depends on the car, but
Oh, okay.
they'll call it a lot of times the OCS,
Oh, okay.
occupant classification system. So it's a sensor that's in the passenger front seat, not the rear seat, generally not the driver's seat. If the dog's driving the car, we got an issue. If a little kid's driving the car, straight to jail. In the driver's seat, generally, if the car's driving, that airbag is going to be full rip. They assume that you're a grown adult driving the car, which probably is going to be changed eventually. That's probably going to get canceled. Yeah, because what if it's a small person? However, they could be adults, and they could probably weigh, I think the threshold was like 110. On the passenger side, though, that's the one that'll be on and off. You can actually mess it up if you put like a heavy thing of groceries or something. Sometimes it can trigger some false issues in codes. But what I've also seen is people would come in and they'd be like, "Hey, my airbag, passenger airbag light off would come on." And
Oh, is that why, like, on the mirror it says on and off
Yeah.
sometimes?
It's
Okay,
measuring,
that
it's
makes
measuring.
sense. I thought mine wasn't working when I saw
No,
it. It
that's
said on.
normal. It doesn't want to deploy that airbag
was like,
unless
is it-
there's someone in there, and unless that
Okay.
person's heavy enough to withstand the impact of an airbag. That's what I mean. If somebody's
Okay.
under like 110 pounds, they're thinking like, do not do a full force airbag. That's probably going to cause more damage actually.
Then good.
Yeah, so it's pretty interesting, but I would see some concerns on this where it wasn't the sensor. I would troubleshoot it and the sensor would be good, but they'd have complaints of this intermittent light, and then I'd have the customer come and talk with me and they'd say, oh, well, it was on a long drive to Lake Tahoe, and I'd say, did you have the seat really reclined? If you recline the seat all the way back, your back weight goes more on the seat back. It kind of takes the weight off the butt, and it would actually make the light be on and off. And I kind of said, well, you're welcome to do that, but you know, the supplemental and restraint system, the airbag system, is really designed. You don't see test dummies hitting the wall and recline. Okay, so by all means recline, but there's no guarantee your airbag's going to protect you in the way that you're hoping if you're laid out like that. You know, this types of thing. So cool systems, cool sensors. Here's that seat pad. This is a strain gauge, so it's actually measuring more or less how much weight is on the seat, and that's why the reclined seat would kind of cause some issues with that. You can't fix that. But the sensors can fail too, and there is a way to program this, and sometimes they'd find that they needed reprogram. We did a lot of programming on these when these were new. Old school cars, this sensor costs money, you know that, right? Old school cars didn't have this. Anybody know on an old school car how you turn the passenger airbag on or off?
No.
You seen
With your
those?
key.
Aren't those cool? You'd be like, you want it on or off? I don't know. Let's do on. Let's do off. And
You're
then they
gonna be
realize
driving.
like nobody ever touches that piece of crap, so we put a sensor in there so that we actually know. But that costs more money, doesn't it? So when you want to be crying about the new cars are too much money, it may or may not be because of the car companies are getting more profit, but it may also be
Because of the
they're
safeties and stuff.
exactly, they're adding this. Now the government's like, no, you need to have a sensor in there. It needs to be automatic. No problem, we'll do it. We're just going to charge the customer. Have a nice day. Do what you
I
asked
still
for.
say remove all airbags.
You can do that, Mr. Jeep. Sign the waiver here. All right, and it showed that injector, the stack of piezo crystals too. Now, electromagnetic, slightly different, right? So that was piezo, this is electromagnetic. Takes place when a conductor is placed in a changing magnetic field. Okay, so if the magnetic field is changing, we can induce electricity in a conductor. Okay, I'm following. This causes an electrical current to be created across the conductor, generating a voltage. Key word, generating. All right, so if we're trying to generate electricity, we can use electromagnetic induction. Okay, we're going to go from there. The current flows one way when the conductor cuts the field in one direction, reverses as it cuts the field in the opposite direction. All right, so if you had, and I believe, okay, if you looked at a generator and we had a magnetic field right here, as it cuts through here, it could generate a positive voltage. As it continues to spin, it's going to go no current. And then as it continues more, it's the other pole of the magnet is cutting the field. That's going to be an other direction, right? See, this one's this way. This one's this way. What did the electrical current just do? How would you use that in a term? It changed directions, right? But what kind of electricity is that?
Alternate.
Bingo. Generators naturally make alternating current. And so actually if this was a sensor and like a magnetic little wheel on the axle, this is how we measure wheel speed. It'd go positive, negative, positive, negative. It'd go positive, negative, positive. Remember how we do the sine wave? Cool. This is a generator right here. If you want to power your house because the electricity goes back out, probably won't because we got that rain, right? But you could hook an engine up to this magnetic strip and force it to turn. And when south passes the North Pole, electricity goes this way. Then when south passes the South Pole, electricity goes this way. And we just have to have a gasoline engine to turn this magnetic thing.
Did you just say something about the rain?
We got rain, so
Yeah, but what does that have to do with?
I don't think that they're going to shut the power off.
But I know,
so
but
I
what
don't
does that
think
have
you'll
to do
need to
with it?
bust the generators out. But if you hear you lose power, you hear people running the generators. Maybe you run your generator. That's this. You hear them start right.
Yeah, I know, but what does that have
The
to do with the
gas
rain?
engine, right? Just because I don't think they're going to lose power again with these high winds because it's wet. I think they're going to be like. I don't think it's going to start a fire. It's wet now, at least for a little.
Oh, okay.
Just the dryness.
Okay, I get you.
Not for the electricity.
Okay, I was like, what?
Simply because the
Okay.
dryness.
All right, I'll get you.
Gas engine goes right here. The gas engine's crankshaft literally turns. In here it'd be a rotor, and the rotor will be spinning. That's why the gas generator creates electricity, because this right here, boom, just like that. That's your electromagnetic induction. So that's kind of what this, we just backed up a page. That's kind of what this says. Remember, the current flows one way when the conductor cuts the field, right? So as it's coming, it's going to flow one way, and as it's going, it's going to change the other way. That's the main reason I think that our houses are mostly AC. I think they figured out the grid in a way where it can be run on big generators, so AC is natural to power in a house because it's running off a generator somewhere at the power plant. Cool. Cars, we don't do that. We store it in the battery, and that's why cars are really DC. Cool, so if we were to move a magnet inside a stationary coil wire, it's going to produce the same effect. So you can do it a couple ways. You can move the rotor, or you can move, I guess let me think of how I'm going to say this. You can move the magnetic part, or you can leave the magnetic part still and move the electrical part. Either way, you just have to have the magnet cutting the electric field. And they've gone back and forth, by the way. They've had it one way and the other way, and they've switched it around. So if you hear like a permanent magnet motor, you know, that's more moving the magnet. Cool. We use this, alternators, that generates the electricity when it spins. Remember we were talking about the magnetic field cutting? This is the part that spins. So what is making this spin? The center part's the magnet. What makes it spin on the car? Exactly, the belt. So when the belt is spinning, what makes the belt spin?
The engine.
What makes the engine turn? Exactly. So right. So if you go way back to the beginning, the pistons are going up and down. It's pulling in air and fuel, compressing it, igniting it, and the energy in the gas and the dinosaur juice makes the crankshaft turn, which makes the belt turn, which makes this turn. So the dinosaur juice is making electricity. Make sense? How it's doing it? The gas. The gas. Should I call it gas? The gas. The gas makes the roundy round. The roundy round makes the magnetic thing go through the electric thing, and it makes the electromagnetic induction, creates electricity, and charges your battery.
That's the simplest thing you could ever say to the most complicated thing you could ever say.
Just happened. That just happened. That's why you need to put the go-go juice in.
Remember, you can use dinosaur juice to go get the dead descendant of dinosaurs to in the shape of dinosaurs to eat.
You talking about dino
Nothing you say
nuggets?
makes sense.
Yes.
Oh, okay. And then the effects, so electricity has unique ability to alter materials, create change, carry out massive quantities of work. We could do a lot with that. You want to make 2 pieces of metal, 1 piece of metal? We could do that. How do we do that? Welding. That's electrical, yeah. You could also use gas technically, but if it's like a MIG welder or a stick welder, that's electrical. You could heat stuff. You could do a lot of stuff electrically, and that's why I'd say it's so valuable to know some of these overall concepts right here. Okay, it could be like heat, chemical, light, electromagnetic. Did you know it could do so much stuff? Now, if I recall,
What other things can it do?
magic and things. The heating effect used in tons of stuff. Heating element, so we're sending electricity through a coil, and that's how I blow dry my hair. Do you believe that?
Yeah.
Yeah, no. I don't do that. That's what happened. Unfortunately, the heating element got too hot and burned it all off. I remember the smell.
I thought it was from pulling your hair on to deal with general mediocrity.
It was having to deal with something, but it wasn't GM. In the second row. And so we could do all sorts of stuff. How about when we send that electricity through that heating element, we call that resistive heating. So houses used to be electro-resistive, right? That's actually really inefficient. New houses are still heated by electricity, but in a totally different way. Electro-resistive was literally the same as a hairdryer. The problem is your house is really big, so you need a really big hairdryer. And that's really bad. That's not good electrically. So then we went into like natural gas or propane. And then there was a couple other things. Now we're actually, if you were to build a new house today in California, they're not permitting natural gas hookups. If you develop a home on just raw land, they're gonna be like, no, you gotta use electric heating. Well, I just told you, electro-resistive heating was really bad for electricity, so why would they go back? They didn't. Your form of electric heating now is called a heat pump. So now we're going to use electricity to run a compressor, which is going to do the whole refrigerant cycle. We got a whole class on that. And that's going to actually kind of generate heat, but what it's really doing is it's moving heat from outside. Even if there's not a lot of it, it's going to gather up the heat from outside through the refrigerant cycle, which is going to make your inside evaporator warm, and then that's going to heat your house. And it's much, 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 much more efficient and also more expensive. So like, if you were to go with electro-resistive hot water tank, $900, maybe less. If you were to go with the new heat pump style hot water tank, double it. It's twice the price. But the electrical usage is about half. So through regulation, they're saying you need these more efficient appliances, you need these more efficient things. But guess what? It's still electrical. It's just not resistive heating. Resistive heating was not real efficient. So if you have an EV, an electric vehicle, you don't want to use a lot of your electricity on heating it, right? So they're using heat pumps, and they're using one more thing. It's what are those red lights called when it's warms? Like anybody had pets? Infrared, right? They actually have infrared technology. So what they found was the heat pump is good, but if they actually put infrared heaters sometimes behind the dash, it'll warm your legs and make you feel warm. Most of the heated seats are still electroresistive, but just so you know, electroresistive it burns up, it's a lot of amps. And volts times amps is watts, and so you're burning watts of energy, and they bill you for that. If you have a new EV, it's probably 100 kilowatt hour battery pack. That means every watt you pull out of it is depleting the battery. You can't go as many miles. So they're trying to be really efficient with the heating types now. Cool. So this is the electroresistive. Cool. That pulls a lot of amps. I think overall makes sense. It's just more showing you the resistance makes heat. So if we had resistance right here, that would actually make heat, and it could melt the wire and melt the insulation right off. That'd make you feel pretty warm. Your car would be real warm.
Will be warm for one more time.
So unfortunately, that's all part of the heating effects. Excessive resistance will cause heat. So like, for example, if the diameter of the conductor is too small for the level of current flow, for example, you put in
Wire's too thin, so it's gonna.
exactly, too thin wires for these big, amazing headlights you got, the heat may actually go into the wire, melt the wire. Well, it's really gonna melt the insulation. And then it could make enough heat to actually start the insulation combustion, which would be fire. Thermal event, if you will. Right, so that's one of the effects. It's good, it's bad. We put a lot of resistance in a heating element so that we can blow dry our hair right off and you'll look like me. Or we can unintentionally add resistance and catch the car on fire. It's a double-edged sword, really. And this, by the way, if current continues to flow through the circuit, thermal runaway takes place. What the heck is thermal runaway? Gets hotter, gets hotter, gets hotter. That's a fire.
Miss
Yeah.
Deborah calling you.
Oh, well, I'll call her later.
Okay.
She knows, she's like, you should be done with lecture. Well, we're almost there. Okay, chemical effects. The chemical effects of electricity depends on the ion. So the chemical effect occurs when electric current passes through a liquid or conductive material. Whoa, that's kind of interesting. When electric current passes through water, water dissociates. What? Into hydrogen and oxygen. You know what this means?
It separates.
Exactly. That's exactly what it means. We can use electricity applied to water to pull hydrogen. Hydrogen is H2O, right? We can pull the hydrogen off of H2O. Do you know what we could do with hydrogen?
Power.
Blow stuff up. Yeah, power stuff. Toyota Mirai, hydrogen fuel cell vehicle. This is the negative. Hydrogen is the most abundant atom as far as we know, I think, on Earth. But this is the problem. I'll give you the problem right now. What's it say right here? When an electric current is passed through the water, you can make hydrogen. So what we're saying is you need to use electricity to extract hydrogen. So like hydrogen's amazing, it's clean, but it takes energy to make the energy. You got to burn electricity to make the hydrogen to then make the car go, and it's sort of like, that's why people skipped hydrogen and went to EV. Make sense? Could we do hydrogen? Yeah, maybe. Here's the cool thing of hydrogen. If you fill your hydrogen tank, sometimes you can go like 500 miles, 600 miles. But you're using electricity to make hydrogen to then put the hydrogen in the car to make it back to electricity. It's just a little like, are you sure this is? I don't know.
Is that why is that why they sell them semi cheap? They use Mirai.
Super cheap.
Yeah.
You can get a Mirai marked down 75%, but you have to apply. Toyota brand new won't just sell you Mirai unless you say, this is where I live, this is where the fueling station is. They're basically letting those cars be experiments. They don't want you buying a hydrogen vehicle unless you're near a hydrogen station. You can't get hydrogen in very many places. That's the problem.
Well, that makes sense. I mean,
Oh shit, these things are so cheap.
where
Super cheap.
Yeah,
That's
I
the
know.
average. Okay, kind of makes sense. That's how we can use electricity to split atoms apart, basically. There's other things that we can do with that, but we'll keep it focused on hydrogen fuel
Bless
cells.
you.
Cool.
Thank you.
Then lead acid battery, kind of similar thing. Electrical and chemical differences in the set of plates create a potential. So this is electricity, how it relates to chemicals. We can use electricity to modify chemicals, and we can use chemicals to make electricity or at least release electricity. So they're very intertwined, if you will. And then again, when we're charging a battery, I want you to keep in mind, as you're charging the battery can off-gas hydrogen, and that's fine, except if you spark near the battery, that can cause one of those thermal events. That can make a big bada boom. You know those? A big bada boom? We don't need it.
An abnormally large thermal event.
Yes. Okay, explosion's a good word for it too. So when we're talking about battery service, I just want you to keep in mind, the reason is when we're charging, it can make chemicals. When we're doing stuff with chemicals, it can release electricity. There's this relationship here. You're charging the battery, it may be off-gassing hydrogen. And then when you connect something and it makes a spark, you may have a, we talked about it. You know what I'm saying?
Yeah.
Cool. All right, pretty good. And then here's like an example of so like a standard incandescent bulb, that's actually really thermo-resistive heating. So we have electricity flow through resistance and it makes heat. Do you agree? That's how the regular incandescent bulb works. If that's a regular, it's not, but if that's a regular light bulb, like the Edison looking cool, pretty light bulb, that's how it makes the light, electro-resistive. LEDs are very different. We're not making light based on heat on LEDs. We're actually using that solid state, an anode and a cathode. We're gonna flow through the LED in solid state, and it's gonna produce a light using very, very little current. It's just an effect. But the LED is not like it's not like a glowing tungsten element. Isn't that kind of different? It's just kind of weird. Cool. So it's making light, but not in the same way. When it makes light in a regular bulb, it's really just making heat. This is an actual effect of the electricity making light. Pretty cool. And then, remember, it's a semiconductor. It creates light by emitting photons from its PN. Remember we talked about the positive, negative, the PN and the NPN, whatever. That's your semiconductor. They produce more light with less heat loss, meaning energy, but also they are cooler, using much less energy. We're using them all the time on cars. New cars have LEDs. It's pretty standard. Used cars, you can buy LEDs and retrofit them. Also pretty common. And then when we talk about electromagnetic effects, so again, the magnetic effect or electromagnetism occurs when electrical current is passed through a conductor. So it goes both ways. How we were generating electricity by passing the conductor through the fields generates. Well, it can be the other way as well. If you were to have electricity flowing through a wire, you will unintentionally create a magnetic field. Did you know that?
Unintentionally.
That's why we can measure this magnetic field and have it indicate the quantity of amperage flowing through the wire. It's hard to have the instrumentation be that exact though, okay? So if you want to measure amperage, you can do an inductive clamp, and all that's really measuring is the magnetic field. The more amps and the more electrons that are flowing, the bigger the magnetic field. We can actually sense that. They also sell some things called like a circuit tester, and you actually just go along the circuit and you just like rub the outside of it and it'll locate the open. The way that, they don't work that good, but the theory of how they work is if there's an open right here, you'd have a magnetic field, magnetic field, magnetic field, no magnetic field. And that's allegedly at least how it's a short finder or an open finder. Or if it was like short to the ground, you'd go over here and there'd be no flow, but here there would be flow because it's short to the ground. It's actually a little more why it's a short finder. Okay, like it. And then again, this all has to do with motor and generator stuff. It's all about the difference. It's all about the relationship of the electrical flow and the magnetic field. Okay, so for example, if you wrap a conductor around an iron core, let's say we do it a bunch of times, you wrap this wire around an iron core. I don't remember if I have a picture. No, I don't. So if we wrap a wire around an iron core a whole bunch of times, it'll actually change the amount of voltage. If you had one core out here and one core in here, you can actually increase or decrease voltage. It's weird. Remember we talked about transformers? How they can increase or decrease voltage? They work on this principle. So the size of the electromagnet is determined by its application. So if we were to talk about that transformer, we can take high voltage and make it into low voltage. Or in the case of a coil that fires a spark plug, we can take low voltage, wrap it a lot of times around iron core, and then if we cut the current flow all of a sudden, it'll induce a very high voltage in the center, and that's how we're able to spark the spark plug. So it's a relationship between the two. Additionally, you guys know what a magnet does with steel, right? You put a magnet on steel and it's attracted or it's repelled, right? What about an electromagnet? If it's not electrified, there's no effect. But if you send electricity to it, it becomes magnetic, okay? I'll give you one. If I press a button and this little thing goes dunk, and then I press the button, it goes dunk, dunk, dunk. What am I doing?
Locking.
Dunk, lock, unlock, lock, unlock. Do you like that game? Is that what you do in the back seat? Lock, unlock, lock, unlock. I love this game every day for hours. If we send voltage one way, if we send current one way through the coil, it can attract. What happens if we send it the other way? Repel, attract, repel, attract, repel. Your power door locks work on this. A lot of things work on this, but that electromagnet, we can magnetize it or unmagnetize it or magnetize it, right? We can actuate your power door locks using this. We could do solenoids. When your automatic transition goes to shift from first to second, we're sending current through a solenoid, which is moving an iron core, click, which is allowing fluid to engage the second gear clutch, and all of a sudden you're in second. And then guess what happens in third? We're like, hey, shift solenoid for third gear. Go ahead and I give you current, you open up, fluid goes to third gear, now you're in third gear. This concept applies to like they all apply. You're gonna see it over and over in different systems. So some of you asked which class should you take next. I told you electrical. You see why? When you go into transmissions and you learn shift solenoids, you'd be like, oh yeah, I remember that ding dong up there talking something about electromagnetic effects of electricity and how you can send current to a solenoid, it'll move a valve and send the fluid or something like that. Remember the unlock lock game? Right? It's the concepts are there. Cool? Same with a fuel injector. You send voltage to it, it'll make a magnetic field, lift a pintle, spray the fuel. What happens if you stop sending current through it? No more magnet, closes off, stops sending fuel. We control valves, injectors all the time using this concept. Even similar with like a starter. We use it with motoring. We kind of talked about motoring a little bit already. Cool. Relays. When we get into relays, when we send current through a relay, it should magnetize the coil and the switch side should go like this. You ready? Click. You ever heard a relay click? You're hearing the effect of the magnetic field. If the relay's got 12 volts in ground, it goes click. And then if you take away 12 volts or ground, it kind of lets go, right? So same concept. You can test a lot of stuff just knowing this concept. So if somebody wants to know about their AC compressor and I haven't turned the AC on and I hear the relay click, I can tell you so much about the car already and all I heard was a click because I know the relay's clicking, which means it's trying to activate the compressor. It tells me half of the problem is, it basically splits the system in half. I know the problem's not over here, I know it's over here. I'm not really that smart of a guy. I just understand the stuff and I know how to apply it. And that's what I'm hoping for. You know the cars don't talk to me, right? I've asked them to, but they don't. But these little details right here can really help me narrow down the problem. And then again, when you want to consider this, we could do when magnetic fields are of flux are passed through a conductor, a voltage is induced. That's like the generator effect. That's how we make the generator. The amount of voltage induced depends on the strength and frequency of the magnetic field. So if you want like a generator that'll power your whole house, guess what? You need a bigger magnet, bigger magnetic field, stronger electricity. That's just the science of it. And then if you increase these, you'll cause more voltage to be induced in the motor. So logically, a bigger motor, bigger conductor, bigger magnet, more power, basically. That's what we're saying. It's got, size does matter. In this case, if you want a bigger motor, you gotta have a bigger motor. It's hard to make more power with the same. Cool. Now with that, you've gotten like a whole lot of stuff thrown at you. A lot of stuff I want you to digest and think about, and you'll see how these concepts will apply to other things. But I'm telling you that no customer is going to jump in and say like, hi, my car seems to not have the correct amount of voltage induced. Do you think it depends on the strength and frequency of the magnetic field? You want to keep these concepts in your mind, but how we're going to actually fix cars is going to change drastically, like in the next couple weeks, okay? Give me different stuff. Okay, our left, you got me. You can hit the full stop button.